our live stream tonight. Sorry, we're a little bit late. I actually fell asleep. I meant to come back from getting food and everything and then starting the live right away, but then I fell asleep, then I took a shower, and here we are. So hopefully we can still say hi to many of you, and we will also continue going live tomorrow and Sunday. But yeah, let's see how this goes. We are here for the taking, as in for the living, for the streaming. I'll show you the book we've been reading, and we will take it from there. And there is Suji over there, so you can keep a watch on what she's doing. Hi, Suji Mama, while I share the live. Today I will chat with everybody first. Oh, it's 1:11 in the morning. It's a full moon today. If you haven't seen the moon, it's very lovely indeed. I got pretty tired after my Boston run, so this is why running late for this live, but here we are. Okay, so I see my live on my other device. I will also share it. Thank you for joining. Love to have you here. Thank you so much. Let's see what we shall be doing today, because I might just chat with you guys and continue the physics discussion tomorrow, or we might do some physics reading depending on who joins. So let's get this party started. Hi, hello. How are you doing? I don't think I can see who is joining, so if you want to say hi in the chat, go for it. Hi, hi. I'ma do my own thing. Hi. Lucky Detective Plays Edits. How are you doing? Thank you for joining. Hi. I'ma do my own thing. I love that username. Thank you for joining. Lucky Detective Plays Edits also says hi. Thank you. Thank you. Thank you. So this Einstein's Cosmos book written by Michio Kaku is something we've been using as a reference to do some discussions. In this live stream, we hang out, we chat, we catch up, we show the kitty cats, there's my voice, and also we do discussions on physics. I've also been showing my face sometimes on these lives now, which is pretty crazy. But that's what's going on here. Generally speaking, we can also just chill for a bit so that we get settled. There's a Royal Bengal tiger right there. Sometimes I call them a loyal Bengal tiger because, well, they're smaller and loyal. So that's what's going on. Here is Baji. I don't know if you can see, but Baji's over here waiting for something. Baji! Do you want treatu? So generally speaking, they like to be given snacks at very regular intervals. They even pretend like they have not been fed sometimes. So all sorts of things can go on here during these live streams. There is Sachi again. So I think everybody's a little confused because we were just now sleeping. I fell asleep and I did not do my live, and I felt like, oh my gosh, I have to do my live. Then I took a shower, and now we're here and we're up. Hello, thank you for joining. We just got started. In a few minutes, we can carry this discussion forward and keep on doing the physics live that we've been doing. I'm putting some lotion on actually because it's very dry. Very dry. How's the weather for you guys? It's gotten very much more dry and colder here in Boston. Oh wow. Look at where Sachi is. Look at where your position is, Suji. Heike, when you join, can you please let me know that you're here? That also would help greatly. I have some regulars of the live stream that join and they want the physics discussion. So I try to get a feel for who is here. Then accordingly, we can get started. Here's the... Some people call this the cat stream. A stream of kitty cats. Like a river. Hi, Fuji Bublai. Hi, Fuji Bublai. Hi. 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 We are pretty tired today, so we might keep it short today, just because I could use some rest. I could use some rest, and hence, we might keep this short. What do you think, Fuji? Are we gonna keep it short? Hi, Sharath. Sharath says, hi, how was your day? Good. Thank you, Sharath. Good. Went out, went to Boston, got some chimichangas, got a drink, walked around, looked at the theater halls, tried to plan out like a show to watch. So yeah. Oh, good. I'm all right, mostly, I think. I just had some allergies. I forgot to take my allergy meds one of the days. Sharath, were you in the live on what day was it? Wednesday, maybe? I know, I was kind of sniffling that day. I think I'm better now. Thank you for asking. I took my meds, sort of the allergy ones, this week. So I think it's gotten better. How's your health? How are you doing? Oh. Thank you. Good to hear. Take care. Yes. Thank you so much, Sharath, for joining and being here. I'm going to get some more water, and then I will settle down on the couch with the blanket and everything, and we might do some reading. Hopefully many of our friends can join and enjoy the discussion. We might also keep it kind of short today because we are tired. But if you're here, then welcome, welcome. Get enough rest. Thank you. Thank you, Sharath. Did you change your username? Because I don't remember this username, and I'm generally very good at remembering. I'm just making sure. Sometimes people join on the live stream with different usernames, and I'm like, wait, is this you? Is this the same you that was the different other? So, anyways, but yeah, thank you so much. You too. Oh, first time here. Oh my gosh. Welcome. How did you know that I was not doing well earlier in the week? Thank you for joining. Well, if it's your first time here, then we must do something special. Yeah, I think my life might be. Oh, how's your voice was kind of distorted. Oh my god. Oh, that's possible. Yeah, indeed. Yeah. Thank you. People are so observant. Wow. All right, Fuji Suji, do you want a snack? Yep, they want a snack. That's why they're running over here. Oh my gosh. Okay, all right. Oh, thank you. Well, you're very observant. Yeah. But anyways, generally when I do my live stream, I feel better. And when we talk about physics, that does help. Where are you from, by the way? I'm from Boston. I'm in Boston. Let me get my water. Hang on 1 second. I need some more water. I'm in Boston. Where are you from? Well, well. All right. So here's Baji. Um, it's been an interesting week, and so yeah, there's been some ups and downs this week. Probably had a few ups and downs today. So in that sense, Sharath is right. I wasn't doing so well, but I think I'll be all right. And um, I did fall asleep. So if you're watching this live later on and you missed it, sorry about that. We ran a bit late today. Um, please share anything you'd like in the live stream chat. And I think what we'll do is we'll keep this live short unless more people kind of join and they want more of the discussion that we've been doing. And I will still cover a little bit of the new chapter that I said I would cover last time from Einstein's Cosmos by Michio Kaku. So we'll get that party started. I'm going to go get more water though first. I'm very parched. So this is where we're at in terms of what we said we would cover. We finished the previous chapter on the unification of the field theory that Einstein was attempting. And unfortunately, we saw that it was not something that was fulfilled, and questions about that are still pending. So he was not able to, especially kind of generalize or find a more generalized theory that could contain quantum mechanics within it, even though at first he was really trying to just unify electromagnetism and gravitation. But then there were also a number of developments in quantum mechanics, and all of that got pretty out of hand, and there were some surprising results. Well, if I let you know my country, probably you're gonna judge. Oh gosh. I'm not very judgmental. Sharath. So I have viewers joining in the live stream. It's very late now in, well, some places, not everywhere. Some places it's early, so thank you for joining from the maybe where it's early places. But I have viewers from everywhere: Japan, South Korea, India, Pakistan, you know, the UK. Where will I judge? I even have people joining from Florida. So I don't think I would judge. So now I'm actually intrigued. Where are you joining from? I mean, there are only so many countries. It could be, yeah, no, I think it'll be fine. I don't think there would be. I'm from India. Oh, well, why would I judge that? Why would I judge that? There's nothing to judge with. Hi, Nicholas. Nicholas is joining from Georgia. Why would I judge from India? What do you mean? I'm from India. I'm originally from India. So I don't judge when people are from India or join from India because that's a lot of people. Thank you so much. I even speak in Bengali and Hindi sometimes, depending on who is joining. But then I think I've other people who don't understand those languages can get a little bit left out. Have you read the last chapter yet? No. We're just getting started, Nicholas, so you haven't missed anything. I haven't started doing the book yet. Some people are racists towards India. Oh, well, that's too bad. That's not fair at all. I will say though, India itself has some racism inside of India, but you're right. People do judge. Yeah, that's too bad. Sorry about that. India. Oh, well, India is one of my favorites. Well, I have both a. No, I don't know. I don't know what I was going to say. I'm always generally happy when I visit. It's just hard to visit, it's very far. The journey takes a long time. I love all people and all walks of life. Thank you, Nicholas. Thank you for your chat message. That's very nice. Whenever I've visited India, it's the place of my childhood, right? So I sort of have a distorted view of it because I've never been an adult there. So I know that my view of it or my experience of it is limited. But in general, I know that it's a subcontinent and it is a very diverse place with a lot of things going on. So I think it would be hard to judge a place like India. I think it would just be ignorant, basically. Not everybody knows everything. So just just not knowing things. Okay. Sorry. Let me get my water. Please hang tight and then we will get into the book. I think that'll be interesting. And if you want to chat and say anything in the chat, then feel free. Today I'm in the mood of reading all of your messages and just kind of hanging out as well. So I think what I'll do is hang out today. Mostly, we'll do some book reading. This is Baji Banerjee and Suji Banerjee right here. Baji, how is Baji doing? Baji was just over there. I think he was monitoring his sister going to the bathroom. They have a new automatic cat toilet, so that's what he was doing. But as soon as I settle down, he'll probably come and sit on my lap. So there is that. Here he is. Sometimes they chase each other at this time. This time of year, the air quality isn't that good in India. Oh my gosh, that's what I was saying yesterday, didn't I? That it was very polluted where I come from, and I got sick. But at the same time, I very much miss the food there and the overall vibe there. So many people, so many things to do, so much. I miss it. But at the same time, I will say, like I was saying, I don't really know it too much as an adult, you know? So my friends who have stayed there as adults, their experience is probably kind of different than mine. Okay. All the kitty cats have gone upstairs, so I might have to show my face here soon if none of the actors and actresses are gonna remain downstairs. Ooh, maybe I'll call them. Ooh, look at Baji. He's bringing his dog toy. Look at that. Look at that. Now they're chasing each other. Suji Mama. Wow. Did you see that? Just wow. Okay, I have my food, or not food, water, and I'm ready. Silly kitties. What? What's wrong with that? Nothing wrong with the. Nothing wrong with the. With that. Okay, Baji, are you gonna come into the mommy lap or what? Baji is over here. So let me continuing from the book. We have been discussing from this book, Einstein's Cosmos by Michio Kaku, how Albert Einstein's vision transformed our understanding of space and time. We actually have made a lot of progress in this book already. We just have a couple of chapters left. So I think I'm going to cover part of chapter 8 here today. It's called War, Peace, and E equals MC squared. In the previous chapter, we saw a lot of bizarre developments in quantum mechanics. Physics took sort of a bizarre and strange turn in some of these progresses. A lot of scientists kind of had difficulties with sort of being on the same page, but they had to accept them anyways. And even some of the contributors of quantum mechanics that made the contribution later on were a little bit hesitant to be a part of it because of the turn that it took. And mainly the issue that people had with quantum mechanics was that it was probabilistic instead of deterministic, which physics was until that time. Until the time of these basically 1920s, 1930s, the physics that most people understood and learned and contributed to was deterministic. The physics that kind of stood the test of time, classical mechanics, classical physics, or Newtonian mechanics, was deterministic, which is that if you had an equation like the position of an object as a function of time, like that of the moon. By the way, there's an amazing full moon today. You could take a look at it. It's very awesome. Hopefully, I think it should still be up. I saw it earlier tonight. So something like the moon or a comet or a planet or a moon of Jupiter even, pretty much the laws of physics and the mechanics that describe these types of things, or you and me, the scale of human beings, kitty cats, cars, trains, those types of things are ruled mostly by classical mechanics. And classical mechanics was long-standing, physics that people understood and accepted, and it had a very deterministic nature to it. As in, if you knew the equation and if you knew the position of something as a function of time at a certain time, you could then predict it for, years ahead, maybe even thousands of years ahead. And that's what people were comfortable with, being able to predict what would happen in the future, being able to say that we understand this system, this might be a complicated system. Maybe there's many objects in the system and it's kind of hard to do the equations, but pretty much we have equations. And once the math is done, I can even tell you something about this system going forward, thousands of years ahead in the future. That was deterministic and classical, and that's what people understood. Even relativity, Einstein worked on special theory of relativity, which is for inertial frames, and then he generalized it to include also accelerating frames and gravitating frames, and came up with the general theory of relativity, which was the more updated theory of gravitation as well, kind of incorporating Newtonian mechanics in it. So he liked this sort of thing, something that can incorporate a known physics already, as if he has come up, and he did come up with a more general theory, which basically Newtonian mechanics is a subset of. It's almost like if you go to this limit, or if you go basically within the scale of our regular life, and if you're not traveling close to the speed of light, then Newtonian mechanics should just fall out of his work, relativity, general relativity. So, this is the sort of thing he liked. And he wanted that sort of thing also to incorporate more parts of physics like electromagnetism, quantum mechanics, and he was pursuing something called the unified field theory. I can understand you better when I can see you. Oh, Reese! Hi, Reese. How are you? I'm so happy to see you here, Reese. It's been awful. This week kind of sucked. How's your week been? Mm. No, yeah, kind of. I don't know. I've just been having a rougher week than usual. Yeah, no. But I was summarizing. So, Reese, you missed the thing that I was just talking about, which is the what you may call. I'm very tired today, so my face is gonna be, I don't know, something. But hope you feel a bit better. Yeah, I do. Here, I'll come into the picture here. So so you missed, Mr. Reese has missed the last chapter. So we're now on chapter 8 of Einstein's Cosmos. And the chapter that I was just now summarizing, there she is. Hi. Hello, my friend. Oh, this has sucked. This whole week kind of went to shit, if you know what I mean. Which is fine. You don't have to know what I mean. I'm just catching up. But today I went out and then I fell asleep and now I'm late and here we are. Yeah. 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 So anyways, you missed the unified field theory discussion. I was just summarizing that. So basically, Einstein liked when something that he worked on could generalize something that was already known, like Newtonian mechanics, when it just can fall out of general relativity in the limit of, in the, oh, thanks, in the limit of our scales, and when you're traveling at speeds much smaller than the speed of light. That's Newtonian mechanics, and those types of results should just kind of come out of general relativity. That's what he liked. That's when he felt like his like his theory was correct. His theory was theorying. Like if his theory can kind of subsume something that was already known, don't worry, things will surely get better. Thank you. Today I got all dressed up and went to Boston and gave myself a nice time. And then I showered and whatnot. But so, yeah. But yeah. Thanks. Thank you. But yeah, anyways, he liked when his theory could just kind of generalize something that was already understood, and it could just kind of fall out of his more general theory. And I think he wanted to do the same thing with quantum mechanics, and he he kind of worked on that. He worked on that with his grad student. We kind of briefly heard about his work with Rosen, and we briefly actually saw the Einstein-Rosen Bridge. I might read that again for you here because Reese is here and he missed it. Hi, Suji. From last night. Oh, thank you. Your words are wisdom and I find it very interesting. Thank you, thank you. But basically, he was trying to come, Shona. This is Suji Mama. Suji Mama is joining me in the chat, in the lab. Wow. Wow, Suji. Suji has presented her butt to me. Great. So he was trying to do a similar kind of thing with quantum mechanics. And he developed something called the Einstein-Rosen Bridge. No, I did not get my... I just got food and drink. My drink had... It was a cocktail. It said bourbon, and I kind of forgot what bourbon was. And so I got it. The cocktail sounded good. It was like, it's a hot lemon something cocktail, whatever. I got dressed up. See, I have all these like rings and stuff on. Usually I don't. This is my going out. Well, I've taken off my other stuff, but I have a few remnants of what I wore tonight. Just got food, drank, walked around, looked at the theater district in Boston. That's it. No petty mani today. I'm saving money. I think I have to do my own petty and mani soon here. Anyways, but yeah, so the stuff that you missed, Reese, are you still here? Shall I read for you let me read for you the Einstein-Rosen Bridge because you missed that. So, Einstein and Rosen proposed a novel way to achieve such a solution. And the solution that we're talking about here, yes, I'm here. Okay, good, thank you. So basically, Einstein wanted to come up with a more general theory for quantum mechanics, something that would include quantum mechanics in it. Because he wasn't liking the turn that quantum mechanics was taking. The new quantum mechanics was something that required physics to be probabilistic, for results to be probabilistic, and for uncertainty to be a thing, and for uncertainty to not only be a thing, it was theorized and was formalized as a thing. So, sounds delicious. Yeah. So he was not at all happy with that. Not at all happy. So you, Reese, we talked about this for the last 2 days, Wednesday and Thursday night, sort of here-ish time. But basically, there were a lot of big developments in quantum mechanics in the timeline of 1920s and 1930s, some of which, you know, Einstein was agreeing with or more okay with, and some of which he even kind of debated. And he gave Bohr, for example, Niels Bohr, one of the pioneers of quantum mechanics, sort of a very hard time because he wasn't sort of good with these types of developments in quantum mechanics. It was hard. It was hard for a lot of people, and some of it was hard for Einstein too. So we had an interesting discussion of where we saw a lot of people, a lot of physicists, as great as they can be, they can also have difficulty accepting new things, especially when they're so different from what they're used to. And so quantum mechanics is an example of something that gave even Einstein a hard time with regard to how bizarre it became. And let me give you a few examples of the bizarreness. So pretty much, so remember, actually, Reese, you were here when we, I'm trying to remember the last time you might have heard something that we were talking about. And I think it was already getting a little bit more strange at that time, but I'll give you a flavor for what's really strange. So Basically, I just told you in summary, not going into the full drama of it, because the full drama of it is covered in the last 2 days of my live streams, which you're most welcome to catch up with under the live tab. But basically, there was a lot of really ridiculous things happening in quantum mechanics. Very strange things, because nature is strange. One of the things that then he came up with as far as what was really troubling him is in the following paragraphs. So let me just read that. So, I have thought 100 times as much about the quantum problems as I have about general relativity theory. So he was very invested in quantum mechanics as well. Wrote Einstein about how he endlessly grappled with the foundations of the quantum theory. After much deep thought, Einstein fired back with what he thought was the definitive critique of the quantum theory. In 1933, with his students Boris Podolsky and Nathan Rosen, so this is the Rosen of the Einstein-Rosen Bridge that we'll talk about as well, he proposed a novel experiment that even today is causing headaches to many quantum physicists as well as philosophers. The EPR experiment. Oh, Einstein, Podolsky, Rosen, EPR may not have demolished quantum theory, as Einstein had hoped it would, but it succeeded in proving that the quantum theory, which was already pretty bizarre, gets weirder and weirder. So this is just to kind of reaffirm that if you find quantum mechanics to be kind of weird, you're not alone. Even Einstein thought it was really strange and bizarre, and in fact, he had so much issues with it, he even wanted to kind of demolish it, like get into thought experiments that would really question it and maybe kind of break it down, but it just kept getting weirder and weirder, and it didn't really get broken down. But here's one such attempt. Suppose that an atom, okay, so listen up. Suppose that an atom emits 2 electrons in opposite directions. Okay, suppose that an atom emits 2 electrons in opposite directions. Each electron is spinning like a top, pointing either up or down. So spin is a fundamental property in quantum mechanics of particles. Electron is a fundamental particle. It has, of course, a property called spin. We can read more about spin, but for the moment, let's just say that spin is such a property, and we can measure it in quantum mechanics. So this is the thought experiment that Einstein is coming up with his students. Suppose that an atom emits 2 electrons in opposite directions. Each electron is spinning like a top, pointing either up or down. Suppose further that they are spinning in opposite ways. So the total spin is 0, although you don't know which way they're spinning. So all we know right now is that the total spin is 0. And because the total spin is 0, for this system, the spin will be conserved. It will always stay 0. That's a property. Okay? So now suppose further that they're spinning in opposite ways. Oh, sorry, I already said that. They're spinning in opposite ways, so the total spin is 0, although you don't know which way they're each spinning. For example, one electron may be spinning up while the other is spinning down. If you wait long enough, these electrons could be separated by billions of miles. Before any measurement is made, you don't know the spins of the electrons, okay? Are you ready, Reese? I get uncomfortable around women then. Well, this live stream will be a great opportunity to get more comfortable. Now suppose that you finally measure. So there's spooky action. Yes! You know about this? Yes! Reese, how did you know about this? Yes! Ah! Isn't that so cool? No problem, Nicholas. It's gonna be great. How did you know it's spooky action? It's famous, right? This is very famous. Now suppose that you finally measure the spin of one electron. It is, for example, found to be spinning up. Then instantly you know the spin of the other electron, although it is many light years away. Since its spin is the opposite of its partner, it must be spinning down. This means that a measurement in one part of the universe instantly determined the state of an electron on the other side of the universe, seemingly in violation of special relativity. Einstein called this spooky action at a distance, just like Rees said. The philosophical implications of this are rather startling. It means that some atoms in our body may be connected with an invisible web to atoms on the other side of the universe, such that motions in our body can instantly affect the state of atoms billions of light years away, in seeming violation of special relativity. Einstein disliked this idea because it meant that the universe was non-local. That is, events here on Earth instantly affect events on the other side of the universe traveling faster than light. So basically, this whole concept of something traveling faster than light was very disturbing. But later on, we kind of talked about it. It's not that the information passed, faster than the speed of light. It's just that we know. Knowing something is not the same as information traveling at speeds faster than the speed of light, which would be odd. And we decided that we're fine with it. I decided I'm fine with this, even though this is kind of mind-boggling for people even now. So anyway, on hearing of this new objection to quantum mechanics, Schrödinger wrote to Einstein, "I was very happy that in that paper you have evidently caught dogmatic quantum mechanics by the coattails." So Schrödinger, again, another huge contributor of quantum mechanics, was also kind of not happy with it because of the developments happening in that field. Hearing of the latest Einstein paper, Bohr's colleague Leon Rosenfeld wrote, "We dropped everything. We had to clear up such a misunderstanding at once. Bohr, in great excitement, instantly began dictating the draft of a rejoinder." You should ask questions at the end of each story to make sure that people are still listening. Yeah. Hi. Hi, Chloe. Okay, so I see Chloe, Nicholas, and Reese. Good. All my friends, all my late night friends. The Copenhagen school withstood the challenge, but at a price. Bohr had to concede to Einstein that the quantum universe was indeed non-local. So this is all very strange. Physicists were not used to... yeah, you'll see. It's basically, this is it. This is what it is. Bohr had to concede to Einstein. So Bohr is Niels Bohr. So he's kind of on the quantum camp. There's the people who are on the Einstein camp of not really liking quantum mechanics and its developments in the direction of the very, very bizarre. And then there's the people on the Bohr camp or the Niels Bohr camp or the Copenhagen school. So you'll hear about that right now. So Bohr had to concede to Einstein. So they're debating. They've been going back and forth here. They've been debating. Bohr had to concede to Einstein that the quantum universe was indeed non-local. That is, events in one part of the universe can instantly affect another part of the universe. Yeah. Everything in the universe is somehow meshed together in a cosmic entanglement. So this is where the entanglement comes in. So, in modern like dating stuff and spiritual stuff, sometimes people talk about like entanglements and twin flame and all that. This is what you can blame that on. This is where it comes from. Okay? So, everything in the universe is somehow meshed together in a cosmic entanglement. So the EPR experiment did not disprove quantum mechanics. Hi, Fixie404. It only revealed how crazy it really is. Over the years, this experiment has been misunderstood, with scores of speculations that one could build EPR faster than light radio, or that we can send signals back in time, or that we can use this effect for telepathy. So these types of things are maybe misrepresented a little bit in sort of information around this topic. The EPR experiment did not negate relativity, however. In this sense, Einstein had the last laugh. No useful information can be transmitted faster than light via the EPR experiment. For example, you cannot send Morse code faster than light via the EPR apparatus. Physicist John Bell used this example to explain the problem. He described a mathematician called Bertelsmann who always wore a pink sock and a green sock. If you knew that one foot had the green sock, you knew immediately that the other foot had the pink sock. Yet no signal went from one foot to the other. In other words, knowing something is entirely different from sending that knowledge. There is a world of difference between the possession of information and its transmission. So basically, all of that to say that it's the pink sock, green sock thing. If a mathematician always wears a pink sock on one foot and a green sock on the other foot, if you saw one foot and you saw it was green, you automatically would know that the other foot had the pink sock. Because you just know this. It's not the same as information being passed from one foot to another. That's the same thing with those electrons. We measure the spin of the one electron, and we find it to be up. And of course, we've probably even changed it by measuring it. And because we know that this one is up, I think so, yeah. Basically, if you change the pink sock for a green sock, it changes the color of the other sock. Yes. Basically, you're taking a measurement. We don't know. So, Reese, the other thing is, in quantum mechanics, remember how when you make a measurement, it changes the state. So, because we make a measurement, we find that the sock is green. First of all, it's green because we made a measurement. And that also instantly tells us, because we know that the other one has to be pink, because this one is measured as green. So same thing for the electrons. If this sock is measured as green, then we know that the other sock has to be pink. If this electron is measured to be up spin, then we know that the other one has to be down spin. It's the pink sock, green sock thing. It's not information. Came for kitten, stayed for history of quantum mechanics. Yes. Thank you, John. Here's a kitten. Oh, sorry. Here's a kitty cat, too. Hi, Baji. Come. Baji might sit on lap. He usually joins these lectures as well. So you see the difference between knowing something and transmitting information. Information cannot be transmitted at speed faster than the speed of light. Einstein had a huge issue if anybody suggested otherwise. But thankfully, that's not what is being suggested in this case. We're suggesting that we know about the pink sock. No information was passed from the foot to the other foot, or the one electron to the other. But in normal culture, spirituality, or even some dating related terminology, people talk about people talk about entanglement and this spooky action at a distance, and things kind of being able to affect something on the other side of the universe. But it's not, you have to be careful about your interpretation of these things. I don't know what Rakesh is saying, John said came for kitten, stayed for. Thank you, John. Please keep staying. Reese said that's the most extraordinary thing. How things change when we try to measure. Yes, that's the most extraordinary thing. How things change when we try to measure or observe what's going on. Rakesh, that's yes, indeed. So basically, yeah, I have heard worse though. I think Rakesh cannot be given the medal for this. Unfortunately, I have seen worse. So, so this always distracts me though. What was I saying? I have to now look at the book. This is why I'm glad that somebody wrote things down. Yeah, anyway, things were good in the sense that information was not passed at a speed greater than the speed of light. That would have been really bad. Already things were pretty bizarre. Quantum mechanics, the whole thing about you know something because you measured it. And then also the fact that when you measure something you change it, because at the quantum scale, at the very small scale, physics of the small is such that when you're using something like photon to look at an electron, you've changed the electron because the photon can impart some of its energy to the electron, for example, because it's all about that scale. The quantum scale being so small means that your tools of measurement, such as, say, photons, is going to affect your measurement of what you measure in quantum mechanics. And this was, oh, look at Baji. This was difficult for people to accept because they were used to classical mechanics where things were more deterministic, and uncertainty generally meant sort of an error in experiment. All right, you might have to be put into timeout, Rakesh. You know, every so often, I have to use these features of YouTube, and thank you for giving me the opportunity to do that. Yay! Rakesh Badial is put in timeout for 24 hours. Bye. Poor little boy. No, the 8-year-olds are very mature here. He can't be 8. There's no way. The 8-year-olds love me. He's not 8. The 8-year-olds like the kitty cats, and they're generally more mature. So, yeah. So basically, it was difficult for a lot of people. So if any part of quantum mechanics is ever troubling, just know that you're not alone. There are lots of people who found it to be troubling. Okay, lots of great people. Even the people who contributed to quantum mechanics, like Schrödinger, found it to be troubling. Okay. All right. All right. So by the late 1920s, there were now 2 towering branches of physics, relativity, and the quantum theory. The sum total of all human knowledge about the physical universe could be summarized by these 2 theories. One theory, relativity, gave us a theory of the very large, a theory of the Big Bang and black holes. The other theory, the quantum theory, gave us a theory of the very small, the bizarre world of the atom. Although the quantum theory was based on counterintuitive ideas, so there were lots of counterintuitive ideas in the quantum theory. For example, this probabilistic thing, the uncertainty thing, the 2 electrons, the spooky thing. No one could dispute its stunning experimental successes. Nobel Prizes were practically flying off the wall for young physicists willing to apply the quantum theory. Einstein was too seasoned a physicist to ignore the breakthroughs being made almost daily in the quantum theory. He did not dispute the experimental successes of it. So he's a very good physicist. Just because somebody has an issue with it doesn't necessarily mean that they are, it just means that it's kind of part of the job of a physicist to try and poke holes at a theory. And then the job of the other theorists or the other physicists to then kind of defend their own theory against the hole poking. It's kind of part of it. It's basically like you come up with your work, then you present it, you publish it. People try to poke holes at it, and you have to defend it. And it can be very difficult, of course, if you're up against someone like Einstein, like in that one chapter, in that one portion that we read, where Niels Bohr and Einstein were going against each other. It's not easy at all. It can be very unnerving and very tiring, very, nerve-wracking. But at the same time, it's kind of part of the process. Because it also, when you communicate your work, even if it's not fully developed, say, it actually lets other people contribute. So you want to kind of get your work to a point where it can be communicated, and then you allow others to contribute to it when you sort of publish it or give a talk on it or even go and do a debate on it. It's actually allowing other people to contribute, and that can put in more resources and talents into the problem, because these are hard problems. So of course we need more people, not less people, to work on them. So this is kind of how it went. Like in the beginning, it was Schrödinger who wrote down the wave equation of matter, and then Dirac who made it relativistic. And then suddenly things just became more and more strange, as then it was Heisenberg who said, no, it was Max Born who said that it was actually a probability of finding the electron, not the electron itself, that was being obtained from the Schrödinger equation. And then it was Heisenberg who theorized and formalized uncertainty into an equation, where, because if Max Born is saying that something is a probability, it's a probability of finding the electron, not the electron. And that actually made the math work out, because when the math of this wave equation was the electron itself, it meant that it could get dissipated into the universe. But when it was the probability of finding the electron, it made perfect sense, because, okay, yeah, the probability of finding the electron is more, closer to the nucleus, and its dissipation into the rest of the universe makes sense. Every opinion matters. Yeah, that's true. Yeah, people can put their opinions forward. It seems we need a way to probe these quantum effects much deeper, like a new kind of microscope that can magnify much more than, say, an electron. Yeah, that's possible. Yeah, that's possible. Could be. But basically, all these different people, because there was a portion we read where Heisenberg was actually not at all on the same page in the past with Dirac when he came up with his relativistic equations of the Schrödinger equations. But then the same Heisenberg later on contributed to the uncertainty principle, because at the point at which you have accepted that it's a probabilistic answer, that it's the probability of finding the electron, not the electron, that is being obtained from the equation, at that point, you have to formalize uncertainty, because probability means that there is an uncertainty, and it's an uncertainty of nature. It's not an uncertainty because you made an error. But at that point, and even now, a lot of physicists or engineers are used to error being a limitation of experiment. Oh, I have to report this number with plus or minus this error, because that's the limitation of the experiment. You can't measure it beyond that point. But this particular uncertainty that we're talking about in quantum mechanics, that uncertainty is an uncertainty of nature, where nature doesn't let you measure something to a certainty, because you're at the quantum scale. At the quantum scale, if you know the position of something, you cannot know the momentum of it as well. Sounds like a Rick and Morty. So yeah, quantum mechanics was the most successful physical theory of our period. He would admit, Einstein, even though he didn't like it. So sometimes something you don't like can still be successful, right? And that's what quantum mechanics was in the 1920s and 1930s to a lot of these more seasoned physicists at that time. Neither did Einstein impede the development of quantum mechanics, as a lesser physicist might have. In 1929, Einstein recommended that Schrödinger and Heisenberg share the Nobel Prize. But it is something about us ourselves that causes the uncertainty. Uh, it is something about us ourselves. What do you mean? He would no longer attack the theory as being incorrect. His new strategy was to absorb the quantum theory into his unified field theory. So, this is where basically he has now understood that quantum mechanics is going to be a thing. Lots of people have contributed to it. There have been lots of breakthroughs in quantum mechanics. It's not something you can just say, oh, it's not a thing. It's going to be a thing. And of course, another thing too is that quantum mechanics as a field is more new, right? Classical mechanics have been around forever compared to quantum mechanics. 1920s, 1930s, that's like less than 100 years ago. So it's actually more new. And whenever something new happens, there's going to be a camp that is like part of the new camp. And then there's going to be a camp that's the more seasoned physicists or the more older physicist camp. And basically, those were the two camps here. And probably the quantum camp is trying to become mainstream at that point and trying to get the recognition and understanding that they deserve, and probably feeling a bit defensive, because they're literally fighting these battles in real time as part of their lives, which is now history. But at that time, that was what they were, going through. Like Niels Bohr, can you imagine? He is up against a living legend, Einstein, like he was just a poor physicist who is young and like trying to do his work, and he's done something that is so bizarre but still like a thing, a real thing, that now he has to go up against someone like Einstein. Just imagine how scary that might have been for somebody like Niels Bohr. They were trying to say is the quantum leap theory is way over our heads. Is it a cop out? We're generating some kind of energy while trying to measure or observe, maybe, which causes a kind of interference on the quantum scale. The uncertainty problem seems like a cop out. So, the uncertainty principle is basically a theorization, it's a formalization. It's basically once you say that the equation gives you probabilities, it also gives you an opportunity to formalize your uncertainty. And this uncertainty is an uncertainty of nature. It's not an uncertainty in the sense of, I appreciate the comment. This exact thinking is what Einstein and others were thinking at that time. They also did not like it. They also thought it was a cop out. But the problem is that it is how it is. It is what it is, in the sense that it's not only it's not only formalized, there's also like a whole equation for it and everything, and it was shown to be right experimentally. It has success, and pretty much like the uncertainty principle, it would not be accepted if it wasn't experimentally tested, basically. And the principle, it's a principle in the sense it was first kind of thought of and then probably it was measured. And the thought is that it's not just a thing that because you can't measure it, it is a truth of nature. And the exact terms of it and the exact equation of it is something that comes from nature itself. It's not, you know, because the equations give you probability. Now you have something like uncertainty principle, and there were a lot of debates about it. It was actually pretty entertaining to read those parts which had the debate and whatnot. But uncertainty principle is, I know, it can be mind bending. What does that mean though? Why would uncertainty be built into nature? Ah, that's a great question. So, so because, so at the very fundamental level, if you're looking at, say, the position, I'm pretty certain, I'm pretty certain everything around me is real. Right. So we're talking about quantum mechanics. In quantum mechanics, again, what are we talking about? Pretty fundamentally, what people try to find is the position, say, of an electron. It almost implies it was designed by something. Yeah, it's a description of something more than a design, if that makes any sense. Basically, it's a thing that happens and we have an equation to describe it. Oh, no, 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 no. It's not like that. And they don't want us to know what's going on. No, no, no. I don't think it's like that. It's not like that. It's not that hard actually. It's literally saying that if you know the position of an electron, you won't know its momentum. And if you know the momentum of an electron, you won't know its position because you've changed it by measuring. It's not that difficult. It's not like that bad of an uncertainty, if that makes sense. Are they with us in the room right now? Who? Who is with us? Even though I believe nothing that I hear and only half of what I see. Basically, if you have used a photon to measure the position of an electron, you've probably given it an extra energy, and now there's an uncertainty in its position. And Heisenberg, all he did, the poor guy, is give us an equation that will give you that uncertainty, right? So it's not really that deep, actually. It's not that bad of a situation, if that makes sense. We can real quick go back to that part though. This part will help. So Werner Heisenberg took this one step further. And by this, I mean that Max Born basically said that the Schrödinger wave equation for matter, because remember, are you religious in any way or no? Who, me? Not super religious, no. Yeah, no, I'm not super religious. I mean, I'm Hindu, born Hindu, can't really control that. But not really. It doesn't conflict with physics anyways. Yeah. So we know that Schrödinger had written down the equation, the wave equation, because remember, they had a bit of a craze with wave-particle duality. So, for example, light has wave-particle duality. So they thought, well, matter might have wave-particle duality, and it did. And de Broglie had a work on that. And then Schrödinger had taken that and gone one step forward and written down the wave equation for matter, or the wave equation for a particle like the electron, giving us the wave equation for an electron, for example, giving us its position as a function of time. But there was a problem with that because the wave equations that Schrödinger had written down were sort of like an ocean wave. It eventually spreads out if left by itself. With enough time, the wave equation or the wave function eventually dissipates over the entire universe. But this violated everything that physicists knew about electrons. So just imagine you have a wave equation for an electron and it spreads out over time. And it says that the electron just dissipates out into the universe over time. That's not a good thing because we know, and we had photographic evidence, experimental evidence of the electron within an atom, right? That it's kind of stays local to the atom. There might be sort of some question about where exactly it will be and when, because it's tiny and it can move a lot, blah de blah de blah. But it wasn't a good thing that Schrodinger's equation was saying that it can just dissipate over time. So then Max Born comes in and says that actually this equation is not the equation of the electron, but the probability of finding the electron. And that actually helped out a lot with the logic and with finding, oh yeah, I know, it's lonely. So something was terribly wrong. Finally, Einstein's lifelong friend Max Born proposed one of the most controversial solutions to this puzzle. This is that electron puzzle, the electron equation. In 1926, Born took the decisive step, claiming that the Schrödinger wave did not describe the electron at all, but only the probability of finding the electron. So remember, Schrödinger wrote down the wave equation of matter. Dirac made it relativistic, but Max Born is the one who said that it's a probability of finding the electron, which is the wave equation, not the electron. This is where we are at this time, okay? Now, if you're saying that the wave equation gives us the probability of finding the electron, and it's very successful in that sense, it successfully describes it, like as in it matches experiment. Because remember, if these findings or these equations or these theories don't match with experiment or experimental finding, then it would have, I mean, can you imagine? These people are waiting to poke holes at your work. If at any point they can poke a hole, they will. You can trust physicists to do that. I've worked with them for a very long time. So I know that if they can poke a hole, they will. So when Max Born says it's a probability, if they could have poked a hole at it, they would have. So it is tried and tested that it's a probability, okay? Okay, I'll read your comments in just a second. Let me finish my thought. Now that we have established that it's a probability, you have to write down something for uncertainty. It just comes out of it. So we must thank Heisenberg, who took it a step further and wrote down the uncertainty. So we'll read about that right now. So and it's a good thing. It's a good thing that it's a probability, because now the probability dissipating over space, over the universe, was fine. So he declared that the motion of particles follows probability laws, but probability itself propagates in conformity with the laws of causality. In this new picture, matter indeed consisted of particles, not waves. Thank God. The markings captured on photographic plates are the tracks left by point-like particles, not waves. But the chance of finding the particle at any given point was given by a wave. The chance of finding the particle was given by a wave. Got it? So when we do quantum mechanics and we write down the chance of finding the particle, that's what we're writing down. Chance of finding the particle. And that's given by a wave. So in all of quantum mechanics, for the whole year that you take quantum mechanics, you have to keep that in mind. You're writing down the chance of finding the particle, which is given by a wave. So it's a little subtle. Quantum mechanics is more subtle than classical, okay? More precisely, the absolute square of the Schrödinger wave represents the probability of finding the particle at a specific point in space and time. Thus, it did not matter if the Schrödinger wave spread out over time, because remember, Schrödinger's wave spread out over time. It's a good thing that this is a probability that's spreading out over time, because that's fine. That's kind of fine, right? That makes sense. It simply meant that if you left an electron by itself, over time it would wander around and you would not know precisely where it was. All the paradoxes were now solved. The Schrödinger wave was not the particle itself, but represented the chance of finding it. Now, the fact that it represented only a chance kind of hurt physicists. Even Schrödinger didn't really like that what he had written down was just a chance. He was not okay with it. I think it kind of hurt people's egos. But nature is more than that. Nature is more complex than hurting people's egos. It doesn't matter if it's okay with people or not, but it is a chance. So we shall continue. Werner Heisenberg took this one step further. So now that we know that we've written down the chance of finding the electron, we must write down the uncertainty. And thank goodness Heisenberg has done that for us. We don't have to. So Werner Heisenberg took this one step further. He had agonized endlessly with Bohr over the puzzles of probability infesting this new theory, often getting into heated arguments with his older colleague. Wait a minute, is Heisenberg younger than Bohr? Shit, I think I missed that. Hey Google, when was Heisenberg born?
Werner Heisenberg was born on December 5th, 1901.
Oh, he was a baby at this time. Hey Google, when was Niels Bohr born?
Niels Bohr was born on October 7th, 1885.
He's like 16 years older. Bohr was older. Oh, baby. Oh, poor Heisenberg was youngy. He was so young at this time. Yeah. Wait a minute. Wait, what is what is 1900 minus 1885? Is that 15? 16. Heisenberg was 16 years younger than Bohr. Oh, that makes so much sense because Bohr did the work with the hydrogen atom. Hey Google, what did Niels Bohr get his Nobel Prize for?
The structure of atoms. On the website nobelprize.org, they say, recognition of his work on the structure of atoms came with the award of the Nobel Prize for 1922.
Yeah. Okay. Yeah. So Bohr worked on atom stuff. We knew that. He debated Einstein. We know that. Schrödinger wrote down the wave equation. We know that. Dirac made it relativistic. We know that. Max Born said that the Schrödinger wave equation is really a probability of finding the electron, not the electron itself, which thank goodness helped a lot because that would have meant if it's for the electron, it would have made it dissipate into freaking space. If it's the probability of finding the electron, the probability dissipating is much, much more fine. And it all made sense. Now we have probabilities. We know that quantum mechanics is a bunch of freaking probabilities. We've written down equations for the chance of finding the particle. And then Heisenberg comes along. He was only born in 1901. He's so young. He's so young. Oh, my poor baby. Heisenberg was born in 1901. Can you believe that? In 1920s, he's so young. Oh. Oh, poor baby. Werner Heisenberg took this one step further. Okay. You guys ready? It's a probability. Heisenberg took this one step further. He had agonized endlessly with Bohr. Bohr is older, 16 years older. It's always those people who are 16 years older. They're just old enough and more mature enough and more established enough where you would have a hard time. But they're not that much older. They're just old enough. Poor Heisenberg. I feel so bad. He had agonized endlessly with Bohr over the puzzles of I'm glad you guys are having a healthy discussion here. He had agonized endlessly with Bohr over the puzzles of probability infesting his new theory, often getting into heated arguments with his older colleague, that is Bohr. One day, after a frustrating night of grappling with the question of probabilities, he took a long stroll down Field Park behind his university because he's a poor baby. Aww. Constantly asking himself how it was possible that one could not know the precise location of an electron. How can the location of an electron be uncertain, as claimed by Born? So this is Max Born with an N. If you can simply measure where it is. So Heisenberg knows that you can measure, right? Like they were getting those photographic plates of the whatever, the electron, the photographed on film. So they kind of they could measure. So Heisenberg is the guy for uncertainty. And just like you guys were saying, like, why can't you just measure it properly? Like, it's a cop out. I understand. That's what they thought too. These people are smart. They thought the same thing, right? When you think so much about a thing to the point where it makes you mad, that's what's happened here to Heisenberg, poor baby. Then it suddenly hit him. Everything became clear. In order to know where an electron was, you had to look at it. Like you can see me now, it's because the photons are it's because the photons are helping to illuminate me, refracting off of me. So in order to know, but now if you're looking at an electron, it's a much different situation because an electron is very tiny. In order to know where an electron was, you had to look at it. This meant shining a light beam at it. But the photons in the light beam would collide with the electron, making its position uncertain. In other words, the act of observation necessarily introduced uncertainty. He reformulated this question into a new principle of physics, the uncertainty principle, which states that one cannot determine both the location and the velocity of a particle at the same time. So that's what Heisenberg did. I know that when people say, when people get it sort of, when people are, it can be hard to mix. That's why it can be hard to get it straight, basically. That's why I think the historical step by step is nice to understand, because it's not like these people liked uncertainty or probabilities. It's just how it is, These people were doing their best with the physics and with what they were getting. Yes. We don't need a better microscope. We need to be able to see in the dark. Yes. You got it, Reese. That's right. That's right. Maybe there will be a different way to see the electron. But you know what the problem is, though? Even if you see the electron with a different particle, because light is a type of particle. Yeah, all educational and fun. Yes. Thank you, Nicholas. Yes, I like your healthy discussion. Have an argument or two in the comments. Why not? If it's about physics, it's all allowed. In fact, physicists love to fight. If there's a fight happening, I'm going to read the comments. But if there's a fight happening with something, that's healthy. That's actually very normal. Do you think these people did not fight? They fought a lot. They fought publicly. Bohr had a whole public debate with Einstein, and it was horrible for Bohr because Einstein was a very good speaker and debater. Heisenberg had fights with Bohr, turns out, and then he came up with the uncertainty principle, probably sufferingly, like he probably wasn't happy about the uncertainty principle, but it came from suffering. More precisely, the product of the uncertainty in position and momentum must be greater than or equal to Planck's constant divided by 4 pi. So basically, what I was saying earlier is that because of probabilities, uncertainty had to be formalized. And that job was done by Heisenberg. So we can thank him for that, but it's not his fault. He simply put into an equation or put into words what was already there in nature. You know, this whole thing about looking at an electron and needing to shine a photon on it, and the photon, because at those scales a photon can make the electron's position change, and now you've introduced an uncertainty. There's an uncertainty in the measurement because of just how it works. That's the nature part. The nature part is, yes, we shone a light on the electron to look at it. In those photographic plates, that's basically photons, right? That's basically photons being shown at an electron in order to illuminate it and then take a picture of it, basically. When you take a picture of something like this, this is an illusion. For all you know, I look like something else. This is the photons being shown onto me and doing something, and then some picture is made out of that. And so when a picture is made of an electron at those scales, electron is so tiny, 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 tiny. A photon introduces uncertainty in the position of an electron because of the tiny, tiny scale. And so there will be an uncertainty in measuring it. And it's not how well you can measure it. It's not the error of the experiment. It's the error because of how it's the natural. It's a natural error, if you will, because the photon is a natural thing. Electron is a natural thing. That's what that means. So hopefully now that kind of helps with the uncertainty principle and probability stuff that we reviewed here. This was, and again, if you're feeling uncomfortable with any of this, it's because everyone was uncomfortable with all of this. Even the great people who contributed to this field were very mind blown by all of it. So you're not alone if it's a little bit disconcerting. This was the decisive moment when the quantum theory plunged into deep, totally uncharted waves or waters. Up to then, one could argue that quantum phenomena were statistical, representing the average motions of trillions of electrons. Now, even the motions of a single electron could not be definitively determined. Einstein was horrified. He almost felt betrayed, knowing that his good friend Max Born was abandoning determinism, one of the most cherished ideas in all of classical physics. So this is what I was talking about earlier, is that this was very hard for the classical physicists, the older physicists, because they were used to determinism. They were used to having an equation be able to predict something forever, for thousands of years, deterministic. It's like when you have an equation, it should determine, it should give you the truth, and it should be able to predict the future state of that thing, like the moon, the comets, the planets, the sun, in classical physics, these things are deterministic. When you know the position of the moon right now, you can tell the position of the moon. That's how there's a full moon today, and people knew that there would be a full moon today because people know about its position as a function of time for years and years into the future. No, there's bigger problems. So you'll see. Basically, he couldn't come up with something that could cover everything. Basically, it wasn't the uncertainty necessarily that was the problem, but only the uncertainty. But yeah, it was very hard. So we'll get to that part. Basically, a lot of people had trouble with this whole thing, and they were used to determinism. Now everything is probabilistic. There's uncertainty. It's just different. But that's not the only reason for why the unification theory was not possible. So Reese is asking, so does this mean that a unification theory is not possible due to this quantum? No. The unification field theory is very difficult. Basically, we can try it. It's still not a thing yet. The unified field theory is still not a thing. So if you and I want to try working on it, if everyone here wants to try working on it, you're most welcome to. It's not a thing yet. That's because it's very difficult. It's very, very difficult. He tried, so we'll read about the part where he tried. But basically, quantum mechanics now, so in the beginning, he was trying to unify just electromagnetism and gravitation, and already that was very hard. Now he's also having to unify quantum mechanics, and that's very, very hard. Quantum mechanics developed as a whole field. It developed like a crazy thing. So many people contributed to it. All these different properties were now there. The spin being one of the properties, remember, the charge, the mass, the this, the that. There's a lot going on in quantum mechanics. So it's just difficult to come up with a general theory that can contain it, where quantum mechanics would now just fall out of it naturally, and also capture all of these different properties that we know about, because we want to be able to measure those properties. Because remember, quantum mechanics is, it's all these probabilities and whatnot, but when you measure something, that's like a property, right? So you want to still be able to have all those like experimental evidences and successes. Like if you want to derive quantum mechanics from, say, a more general theory, you better be able to show that the results that we know and love from quantum mechanics, though, even though the things are bizarre, but the experimental evidences that came out of what we found in quantum mechanics as that field developed, it better also fall out from this new general theory, right? And that is very difficult. It was too difficult for him to come up with a unified field theory because it's just very difficult. That's why it didn't happen. It's nothing to do with the uncertainty, really. But I think he would have liked for a general theory to not need the uncertainty part. Like, I think he wouldn't have minded if some general theory gave us the physical insight for the meaning, you know, for all of this that then quantum mechanics falls out of. And if it didn't need uncertainty, then I think he would have been happy. But it's not that that was the reason why he didn't have a unified field theory. He didn't have a unified field theory because that's incredibly difficult to do. So physicists were beginning to divide into two camps. Einstein led one camp, which still clung to a belief in determinism, an idea that dated back to Newton himself and guided physicists for centuries. So, you know, for centuries we had everything deterministic, and now we had probabilities. So that was huge. Schrodinger and de Broglie were allies. The other, much larger camp was led by Niels Bohr, who believed in uncertainty and championed a new version of causality based on averages and probabilities. Bohr and Einstein, in some sense, were polar opposites in other ways. So now that there was this big debate between Bohr and Einstein. Do you guys want to hear about that? I know I've covered it already, but it's very dramatic. It's very dramatic. Do you want to hear about it? I'll take a sip of my water. Yeah. Mm-hmm. Okay. So, Einstein freaking hated the uncertainty stuff. Freaking hated it. So, he basically challenged. Of course it's real. What do you mean? Yes, it's real. I do think that physicists have done a bad job of communicating to the public. Otherwise, I think more people would know. This is why this channel exists. I'm doing that job of communicating. Uh, If our eyes are not real? Okay, what was this debate about? That's right, there was no explosion but a fast. Yes! That's awesome, John. I'm just reading the comments above. So you asked, are you religious? I said, not really. I'm not either, but it seems kind of sad in a way that all these things are just an accidental eventuality of an explosion or a big bang. And then John said there was no explosion but a fast expansion of space. Explosion happened in a medium and there was none during the Big Bang, which is another misnomer. Yes! We talked about how the Big Bang is a misnomer. A lot of people didn't like that name. It was not big and not a bang. Thank you, John. To get say the human eyeball from the Big Bang is like throwing a bunch of paint at a piece of paper and creating the Mona Lisa. Hi, Callie. If you're still here, hello. A singularity then, not an explosion. Complexity emerges from very minimal conditions. Read more math. Okay. So there's no kind of ripple in the universe that makes it so that there's fundamental uncertainty. That's right. Yeah. Hopefully what we covered helps with the uncertainty and the probability stuff. Okay, you're right. Okay. That's just a meme from Will Smith's son. And why do we dream? What is vision and matter without consciousness? Oh, wow. You guys ask very good questions, more like philosophical questions. I guess because people like philosophy, um, our PhDs are called doctors of philosophy. But we're not that great at philosophy in the end. We just know physics. Okay, so I'll keep going. I'll keep going about this dramatic event between Bohr and Einstein. Okay? I'll skip to the showdown part. Look at Baji. So, the showdown finally came at the 6th Solvay Conference in Brussels in 1930. What was at stake was nothing less than the nature of reality itself. So just like you guys are talking about what is real and what not, guess what? Einstein and them were also talking about this. They were also very perturbed, very deeply affected by all this probability, uncertainty, you know, even though it's kind of simple, and we have the benefit of history and all these developments and all these confirmations with experimental evidence. But at that time, things were still new, right? So Einstein and Schrodinger, these people didn't like that you had probabilities now, the chance and the uncertainty, all of this stuff. This was hard for them, and they wanted to contest it. They wanted to challenge. It's not. Okay, I'm sorry. No, no. You're great. You're great. Thank you for being here. All right, listen to this drama. Honestly, physicists can be kind of dramatic. They can kind of create drama. And they did. So, what was at stake? So, there's a conference happening. There's a stage. There's Einstein on it, and there's Niels Bohr on it. They're two very different people. Niels Bohr was an introvert. Apparently, he liked soccer, if I'm not mistaken. Einstein was not into sports. Niels Bohr was an introvert, very shy, kind of like mumbled, had a very interesting approach to writing papers. He rewrote them a lot. He got his kind of team of grad students and lab members to kind of keep on writing and rewriting, writing and rewriting drafts. He was very sort of a perfectionist in that sense. Einstein was very elegant, amazing speaker, communicator. Once he would get these elegant ideas. It would come out all like well formed. He would write an amazing, elegant, kind of like Mozart, like it comes out amazing. Then it's published and it's still amazing and it stands the test of time for hundreds of, well, it's been sort of just over 100 years for some of his stuff, but he was very like, comes out, writes down, done. Niels Bohr was like, I'm going to keep on keeping on. I'm going to keep on drafting this to death. So two very different people and in two different camps. Niels Bohr is in the quantum camp, the probabilities and the uncertainty camp, and Einstein is in the more classical camp. Even though he's an old contributor to the old quantum mechanics, because remember, he contributed, of course, to photoelectric effect, which is the old quantum mechanics telling us that light too has a particle nature. It is made up of photons, giving us the photoelectric effect. That's what he got his Nobel Prize for too. So he's considered to be one of the old quantum mechanics contributors, but then there's the new quantum mechanics contributors like Niels Bohr, Schrödinger, Heisenberg. I don't want to put Schrödinger in that camp because he too had issues with some of this uncertainty stuff. But now there's a stage and Bohr is on it and Einstein is on it and they're facing off. Okay, a physics face-off. Einstein hammered incessantly at Bohr, who reeled under the constant attacks, but managed to ably defend his positions. So just imagine Einstein is hammering at you. That's hard. I feel bad for Niels Bohr. Einstein was a very, very good speaker. Very, very articulate, very like he could reason things really well. So like to debate him, it's probably like a nightmare. That's probably like, even if you knew everything, you probably wouldn't want to debate him, And that's what Niels Bohr was doing here. Finally, Einstein presented an elegant thought experiment, which he thought would demolish the demon, the uncertainty principle. So here's that thought experiment. And you guys can also think and tell me what you thought of this thought experiment. Imagine a box containing radiation. There is a hole in the box with a shutter. When the shutter is opened briefly, it can release a single photon from the box. Thus, we can measure with great certainty the precise time at which the photon was emitted. Much later, the box can be weighed. Because of the release of the photon, the box weighs less. Because of the equivalence of matter and energy, we can now tell how much total energy the box contains, also to great accuracy. Thus, we now know both the total energy and the time of opening the shutter to arbitrary accuracy without any uncertainty, and hence the uncertainty principle is wrong. So this is what Einstein is saying, is that I will know the time of this happening and I will know the energy of it. So we don't need uncertainty. That's what Einstein is saying. Einstein thought he had finally found the tool to demolish the new quantum theory. So he's poking holes. He's poking holes with this with this thought experiment. So are you guys good with it? You see Einstein's side of things? There's a box. He's going to release a photon from it at a specific time. He can measure the energy of the box to arbitrary accuracy. He's saying there's no uncertainty about this whole thing. That's his view. That's his take. And Bohr has to debate this. Bohr has to come up with the refutation for this and be like, no, the uncertainty principle is a thing, but he can't. He's struggling because, he's in that moment, he's on the spot, on the stage, there's an audience, and Bohr is like, well, shit, I can't do it. I can't think of a refutation to this. So he was struggling. Paul Ehrenfest, another famous person, scientist that we know, was one of the participants in this conference. Einstein mic dropped. That's exactly right. Einstein was like, I'm going to thought experiment the frick out of this. And Bohr, oh my God, Baji. Baji's on my lap. And I can't move my legs. Oh my God. Ah. Einstein mic dropped with a thought experiment. He was famous for these. He was famous for his thought experiments, right? And they were so clever that you couldn't easily refute them. Because, like, what are you going to say? Like, in the moment, on the spot, and Einstein has elegantly put his argument before you. So, anyway, Bohr was there and he was struggling. And one of the audience participants, Paul Ehrenfest, is saying, so this is a quote from Ehrenfest. He said about this fierce battle, to Bohr, this was a heavy blow. At the moment, he saw no solution. He was extremely unhappy all through the evening, walked from one person to another, trying to persuade them all that this could not be true. Because if E was right, Einstein was right, this would mean the end of physics. So to Bohr, this was the end. You know, he felt so bad. He could not come up with a refutation in the spot, in the moment. No. Elon? Come on. He's all right. He's all right. He's all right. Einstein? Oh, come on. No way. He has good people working for him, though. There might be an Einstein in his working space. Is it? Yeah. Good leader. So, can you imagine that your theory? So, for physicists, the theory is very important. That their work is very important. Being able to defend their work is very important. Einstein just mic dropped on Bohr, and Bohr did not have the refutation in the spot. He's feeling terrible. It's like, we all get, I speak about this example of getting asked a question in your defense that you cannot answer. There's usually one, at least, in the end, that you cannot answer. And you're like, oh shit, I'm going to fail because I didn't know that. It's like that, but probably 1,000 times worse because this is being attended by a lot more people. He's on the spot. I felt so bad when I read this. Bohr had an awful time that night, but he could think of no refutation. I will never forget the sight of the two opponents leaving the university club. Einstein, a majestic figure, walking calmly with a faint, ironical smile, and Bohr trotting along by his side, extremely upset. Oh, poor Bohr. Oh my gosh. When he talked to Ehrenfest later that evening, all Bohr could mumble was one word. Over and over again, Einstein, Einstein, Einstein. But after an intense, sleepless night, are you ready for Bohr's comeback, guys? If you're a mastermind, would you do it all yourself or would you hire people and teach them? Yeah. Teaching is part of the job for physicists, for sure. Trotting along with his tail. Reese, are you ready for Bohr's comeback? Bohr did not know the answer and the refutation at that time, but he spent a sleepless night as you would as a physicist who's just been harassed. I feel so bad for Bohr, I might cry. But I'm so proud of him because look at his comeback now. After an intense sleepless night, Bohr finally found the defect in Einstein's argument, and he used Einstein's own theory of relativity to defeat him. Are you ready? Bohr noted that because the box weighed less than before, it would rise slightly in the Earth's gravity. But according to general relativity, time speeds up as gravity gets weaker. Remember? For example, time beats faster on the moon, for example, because it has weaker gravity. Thus, any minuscule uncertainty in measuring the time of the shutter would be translated into an uncertainty in measuring the position of the box. You cannot therefore measure the position of the box with absolute uncertainty. Furthermore, any uncertainty in the weight of the box will be reflected in uncertainty in its energy and also its momentum, and hence you cannot know the momentum of the box with absolute uncertainty. When everything is put together, the two uncertainties identified by Bohr, the uncertainty in position and uncertainty in momentum, agree precisely with the uncertainty principle. Take that, Einstein. So he used relativity. Everyone has a blind spot. Even though, even though, so just look at this. Relativity was Einstein's theory. But people can have a blind spot even in their own theory. People can still miss something. This is why you must not ever take whatever someone is saying for the face value. Think it through yourself. Learn a topic so well that you can contribute to it. Basically, Bohr is such a good student of relativity. Bohr did not come up with relativity. He's not the one who is obviously credited for relativity. Just because Einstein is credited for relativity, and he did come up with relativity, and that's an amazing thing he did, but that does not mean that he will always have all the answers. We cannot depend on one guy for everything, ladies and gentlemen, especially ladies. We cannot depend on one guy for everything. You can't just be like, oh, Einstein is always right. He will always know everything about relativity at all times. No, he missed this part. So Bohr, being a great student of relativity, caught what Einstein might not have. And of course, he had the investment. It's also about where are you invested. Bohr is invested in the uncertainty principle because it is part of quantum mechanics, which he is a father of. So of course, he wants to work it out. No, he wouldn't do that. Einstein already knew the problem with his thought experiment, didn't bank on it being rumble. No, that would be vicious. No. Physicists are a lot of things. I don't think that they are socially apt enough to be vicious. I don't think they would do that. I don't think he would do that. I don't think he would do that. Yeah. Physicists are like little kids, smart little kids. They don't really grow up. So I don't think you would do that. They're just playing. This is still play. You know how kitty cats fight? That's how Einstein and Bohr were fighting. It's not that deep. Poor babies, they were fighting. But yeah, Bohr understood relativity really well. So he was able to figure out that this gravitation thing, the box's gravity changing actually gives us a way to have uncertainty. Exactly. Too autistic to be that manipulative and nasty. That's funny. Yes. Of course, they're weird. They're socially weird. Why would they be manipulative and nasty? That's like the only thing that physicists can't do very well. And we also cannot tell when we're being manipulated. Very bad. Very bad. Yeah. For certain normal things, normal relationships, normal what's acceptable, what's not acceptable, like dating and things like that. It's very difficult for physicists. So it's good when they find somebody who can kind of like take care of them, like a child, because that's kind of how it is. Yeah. Anyway, but Einstein, just missed the part about the box's gravity because he's not always thinking about relativity. Even though he's the guy for relativity, you'd be surprised. It's like he's a genius, but he's also human, and human beings can miss things. Human beings all have blind spots. Um, yeah, they can be abrupt. Yeah, how do you know that? Yes, that's a thing. That's a thing as well. Sort of like the social things are a little hard, you know? So, you're laughing? Oh, good. So, he just missed it. He missed that when he said it was his own experiment, his own thought experiment that said that the gravity of the box, or that the box's weight would change or the energy would change. But that also means that the gravity of it changes, and the gravity of it changes meaning that the time of it changes, because time is slower now, and that introduces an uncertainty in the measurement of its position. So Bohr won this round. Guilty of being unintentionally abrupt. Physics is hard, but people are stranger. Very true. I think the brain and neurosurgery is probably very hard. Physics is not that hard. Indeed. So when Einstein complained, so Bohr had successfully defended the quantum theory. When Einstein complained that God does not play dice with the world, so this is a famous quote of Einstein. He said, when you hear that quote, Einstein said, God does not play dice, he meant probabilities and uncertainty. But the thing is, this was Einstein's view. God does not play dice with the world. Bohr reportedly fired back, stop telling God what to do. In quantum mechanics, God does play dice. So ultimately, Einstein had to admit that Bohr had successfully refuted his arguments. Einstein would write, I'm convinced that this theory undoubtedly contains a piece of definitive truth. Commenting on the historic Bohr-Einstein debate, John Wheeler said it was the greatest debate in intellectual history that I know about. In 30 years, I've never heard of a debate between two greater men over a longer period of time on a deeper issue with deeper consequences for understanding this strange world of ours. So that was that debate. It is. It's late, isn't it? So, this sort of thing was going on. But then they had to accept the uncertainty principle and quantum mechanics's developments. And pretty much, then I also told you about the spooky effect as well. So you already knew about that. The process of observation determines the final state of an object. These types of things were upsetting. Several upsetting. So I'll read this part, kind of skipping ahead a little bit, because basically Einstein and others had to accept these probability type of stuff and these uncertainty type of stuff. So what, right? What happens next? Several upsetting aspects of this puzzle shook Einstein to the core. So basically, oh yeah, also I skipped over the Schrödinger cat thing. It's too traumatizing to read, but you guys know about the Schrödinger cat problem, right? He's basically saying that the cat has to exist in all these different forms, and until you measure it, you don't know its state. And when we read about that part, Baji was on my lap, and we had to close his ears. So I'm not going to read that part again. It's too traumatic. But basically, there is this notion that in quantum mechanics, what quantum is suggesting is that different things are existing in all these different states, and until you measure it, you don't know the state of it. It's kind of like, where was the part where Einstein said, oh, here it is, we'll talk about it. Okay, this paragraph will be good. Several upsetting aspects of this puzzle shook Einstein to the core. First, before a measurement is made, we exist as the sum of all possible universes. We cannot say for certain if we're dead or alive, or whether dinosaurs are still alive, or whether the Earth was destroyed billions of years ago. All events before a measurement is made are possible. Second, it would seem that the process of observation creates reality. Thus, we have a new twist to the old philosophical puzzle of whether a tree really falls in the forest if no one hears it. A Newtonian would argue that the tree can fall independent of observation. But someone from the Copenhagen school, which is the Niels Bohr school, would say that the tree can exist in all possible states: fallen, upright, sapling, mature, burnt, rotten, etc., until it is observed, at which point it suddenly springs into existence. Thus, the quantum theory adds a totally unexpected interpretation. Observing the tree determines the state of the tree, that is, whether it fell or not. So they're kind of extrapolating the issues of quantum mechanics and its implications to a classical world. Because a tree to me belongs in the classical world. So in my brain, I don't care. Because the tree, see, for me, I'm a little strange in the sense that, oh, hi, Shalon. Shilo N says Hindi, please. Kind of we're talking about quantum mechanics. See, in my mind, this all, the realm of things that is described by quantum mechanics, as long as quantum mechanics does a good job of that, I'm fine with it. If I need to solve a classical problem, I will use my classical tools. If I need to solve a quantum problem, I will use my quantum tools. I don't need this tree to be explained by quantum mechanics. You know what I mean? So I know that people sometimes take a thing and they want to apply it to everything. They want to take a quantum interpretation, which is that a thing has to exist in all its states until you observe it, then you observe it, which also changes its state, and that's the state, That's in quantum mechanics. You don't have to constantly be thinking about that always, depending on. So it's very important to know, ma'am, wait, what? A 1v1 on what? Are you edge? I don't know what that is. I don't know what that is. Is that a game? I think for us, it's important to figure out what type of problem are we trying to solve. For example, oh, how did you know this, Reese? You're so good at these comments. So I think if you say in a classical world, classical tools are just fine. If you're in a quantum world, quantum tools are fine. So I don't let myself get too upset by these types of things because it's fine. It's as long as quantum gives us the tools to work in a quantum. That's okay, no worries. As long as quantum gives us the tools to help us answer quantum questions and questions that require quantum mechanics, I'm happy with it. I don't have these issues. Einstein, from his days at the patent office, always had an uncanny knack for isolating the essence of any problem. He would therefore ask visitors to his home the following question: does the moon exist because a mouse looks at it? If the Copenhagen school is correct, then yes, in some sense, the moon springs into existence when a mouse observes it and the moon's wave function collapses. Over the decades, a number of solutions have been offered to the cat problem, none of them totally satisfactory. Although almost no one challenges the validity of quantum mechanics itself, these questions still remain as some of the greatest philosophical challenges in all of physics. So pretty much, yes, I am from India, Shalon. Pretty much, some of the questions you guys are asking or you might have trouble with, those are some of the greatest philosophical questions just in all of physics. So if something seems a little troubling, we can, of course, discuss it further. And I think the discussions help. And understanding the history of how all of this developed also helps because it tells you the reasoning behind things. But at the same time, just know that these are kind of difficult for a lot of people. So anyway, now he did the EPR experiment, the thing with the thought experiment with the two electrons. So now let's get to the point where the unified field theory is again being looked at by Einstein, and he wants to do something about it, because that's the end of this chapter. So this is the part that you missed, Reese. So I'm glad we've caught you up, and now we're gonna get to the part about the unified field theory that you asked about, which is that why was the, unfortunately, unified field theory never actually came together. Einstein was not able to really come up with something that captures all of the things he wanted to capture, because basically he was hoping for a more general theory that then quantum just falls out of. But that would also mean that all of the features of quantum, all of these different properties and things like that, like spin, charge, mass, all of that would have to come out of the new field theory. And that's very difficult to do. That's why it didn't really happen. But we'll read about that. So, the EPR experiment did not negate relativity. In this sense, Einstein had the last laugh because, no useful information can be transmitted faster than light via the EPR experiment. So good. There's no confusion, at least about that things don't travel. Information cannot travel faster than the speed of light. Thank God, right? That would be bad. For example, you cannot send Morse code faster than light via the EPR apparatus. Oh yeah, we already talked about this, the green sock, pink sock thing. If you knew that one foot had the green sock, you knew immediately that the other sock was pink. Yet no signal went from one foot to the other. In other words, knowing something is entirely different from sending that knowledge. So knowing that one sock is green means that the other sock is pink, because we know that system of that man. He wears one sock green, one sock pink. We measure one sock as green, then we know the other sock is pink, without transmitting any information from one sock to the other. That's called knowing. Information transmission would be different. There's a world of difference between the possession of information and its transmission. So we're good. We're good. I think that's this one. Yeah, sort of. This is a ring I got. Both of the rings I got. Sometimes I go to the Caribbean islands, and they have really good deals on jewelry. I know the jewelers there. So that's where this is from. Thank you. Sort of a lucky ring. Yeah, I like to wear this one. And this one I wear sometimes. By the late 1920s, there were now two towering branches of physics, relativity and the quantum theory. The sum total of all human knowledge about the physical universe could be summarized by these two theories. One theory, relativity, gave us a theory of the very, very large, and a theory of the Big Bang and black holes. The other theory, the quantum theory, gave us a theory of the very small, the bizarre world of the atom. Although the quantum theory was based on counterintuitive ideas, no one could dispute its stunning experimental successes. Lots of Nobel Prizes were being awarded, blah, blah, blah. Now we come to the notion of a more general theory. What was Einstein trying? So, when the army of critics in Bohr's camp accused Einstein of ignoring the quantum world, he fired back that his real goal was nothing short of cosmic in scope. Basically, he was saying that I'm not ignoring quantum mechanics. I'm trying to come up with a theory that will subsume it, that will make it so that quantum is a subset of that, which is the unified field theory. He wanted to swallow up the quantum theory in its entirety in his new theory. Einstein used an analogy drawn from his own work. Relativity did not prove that Newtonian theory was completely wrong. It only showed that it was incomplete, that it could be subsumed into a larger theory. Thus, Newtonian mechanics is quite valid in its own particular domain, something I've mentioned too, which is that in our own scale, in our everyday life, Newtonian mechanics is just fine for our scales, human being scale, cat scale, dog scale, tree scale, car scale, earth scale, moon scale. It's fine. Um, Pretty much, if you have a domain in the realm of smaller velocities, velocities much smaller than the velocity of light, in other words, and larger objects, those examples I mentioned, then Newtonian mechanics performs really well in that domain. So Newtonian mechanics is basically a subset of his relativity theory, and it's fine, right? It's a subset. It's not proved wrong. Similarly, Einstein believed that the quantum theory's bizarre assumptions about cats being dead and alive simultaneously could be explained in a higher theory. In this respect, so he was looking for a higher theory that can just contain quantum mechanics. In this respect, legions of Einstein's biographers have missed the point. Einstein's goal was not to prove the quantum theory incorrect, as many of his critics have claimed. He has too often been painted as the last dinosaur of classical physics, the aging rebel who found himself becoming the voice of reaction. Einstein's true goal was to expose the quantum theory's incompleteness and to use the unified field theory to complete it. In fact, one of the criteria for the unified field theory was that it would reproduce the uncertainty principle in some approximation. He wanted this quantum mechanics equations and results and implications to just kind of fall out of his new theory. Einstein's strategy was to use general relativity and his unified field theory. Hi, Kayla! I'm a nerd now, hypnotized. Aw! Hi, Kayla, how are you? So he wanted to, with his general relativity and his unified field theory, to explain the origin of matter itself, to construct matter out of geometry. Because remember, quantum mechanics is about it starts with matter, right? It's the wave equation for matter, which then later on becomes the wave equation for probability of finding matter, for example, very small matter such as an electron. So when you say that you want to have a more general theory that can give you quantum mechanics just falls out of it, then you actually have to have a theory to describe matter. And that's not easy because remember, his theory was sort of the space-time relativity, the bending of space-time, the gravitation being a bending of space-time, depending on how massive, those things are a little bit different. Those things are a little bit more mathy or geometry-y than quantum mechanics. Quantum mechanics is more like stuff. It's actually like this book. It's a classical object, but it's made of atoms and stuff. And stuff's physics is different than, I don't know, space-time's physics. It's a little different. It's different domains, and that can be I mean, just relativity is the physics of the large. It was the physics of the cosmos. There's the cosmos, and then there is stuff. We're made of stuff, and then there's the physics of stuff. But it's going to be difficult to bring those together. It's hard, and you'll see about that. So in 1935, Einstein and Nathan Rosen, this is one of his students, investigated a novel way in which quantum particles, such as the electron, would emerge naturally as a consequence of his theory rather than as fundamental objects. So as I was saying, it's kind of difficult. Oh, good. It's kind of difficult to suddenly go from space-time type of physics to the physics of quantum particles. So he's basically saying that in his way of looking at things, quantum particles would emerge kind of naturally as a consequence of his theory rather than as fundamental objects. So they may require a very different interpretation, in other words. In this way, he hoped to derive the quantum theory without ever having to face the problem of probabilities and chance. Because remember, he still kind of hates the probabilities and the chance. In most theories, elementary particles emerges as singularities, that is, regions where the equations blow up. Think of Newton's equations, for example, where the force is given by the inverse square of the distance between two objects. When this distance goes to zero, the force of gravity goes to infinity, giving us a singularity. Because Einstein wanted to derive the quantum theory from a deeper theory, he reasoned that he needed a theory totally free of singularities. Examples of this exist in simple quantum theories. They are called solitons and resemble kinks in space. That is, they're smooth, not singular, and they can bounce off each other and maintain their same shape. Einstein and Rosen proposed, so we're almost done with this chapter. Einstein and Rosen proposed a novel way to achieve such a solution. They started with two Schwarzschild black holes defined on two parallel sheets of paper. By using scissors, one could cut out each black hole singularity and glue the two sheets back together. Thus, one obtains a smooth, singularity-free solution, which Einstein thought might represent a subatomic particle. So he thought of quantum particles as tiny black holes, because he needs some connection between the stuff that is quantum particles and his physics that he knows and loves, which is the large-scale cosmos type of physics, like relativity stuff, right? So he's viewing quantum particles as tiny black holes, which is fine. You can do that. In fact, this idea was actually revived in string theory 60 years later. So many, many years later, this idea was revived, but that's what Einstein was trying. Like, this was his efforts in the unified field theory, okay? It wasn't easy. Like, you can do that, but is it going to give you all the things you want? That's the question. So basically, there are mathematical relations that can turn subatomic particles into black holes and vice versa. So, string theorists can also work on that later on, did work on that later on. This Einstein-Rosen Bridge, this is called the Einstein-Rosen Bridge, however, can be viewed in another way. It represents the first mention in the scientific literature of a quiz question. This is the first mention of a word that you know. I know that you know. It connects two universes. Shortcuts through space and time, like a gateway or portal that connects two parallel sheets of paper. The concept of this word that you're gonna guess. No, keep guessing. Wormhole! Yes, Kayla! Yes! Yes, 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 yes. Wormhole. So the Einstein-Rosen Bridge gave us the wormhole. Kayla wins this round. Sorry, I was eating ice cream. Well, Kayla, you were eating ice cream maybe in a different universe, because in this universe, you win. Kayla got it. And John got it. And Reese got it. Yay. So this Einstein-Rosen... Yeah. You all win. You've all passed through the wormhole. This is the first mention of a wormhole. This is it. So Einstein trying to unify quantum into his world, trying to come up with a more general theory of quantum mechanics, making quantum mechanics and particles kind of fall out of his theory, gave us the notion of the wormhole. The energy in our bodies keeps us from falling. Yes, the Pauli exclusion principle actually makes us not fall through. It's a quantum thing. That's a quiz question too. What keeps us from falling through the earth? It represents the first mention in the scientific literature of a wormhole that connects two universes. So all of this work and math that Einstein was doing, trying to subsume quantum mechanics into a general, more larger theory, gave us the concept of wormholes. Wormholes are shortcuts through space and time, like a gateway or portal. The concept of wormholes was introduced to the public by Charles Dodgson. Yeah, yes, sort of, where two things cannot exist in the same. Yeah. Okay, wormholes appear in popular literature? Which famous book has a wormhole? Hey Google, can you make your volume 50%? Hey Google, can you tell us what is the Pauli exclusion principle?
On the website chem.libretexts.org, they say, the Pauli exclusion principle states that in an atom or molecule, no two electrons can have the same 4 electronic quantum numbers.
Sort of the deeper reasoning is that. The deeper reasoning is that's why we can't fall through. Okay? So, okay. Where does the wormhole, you guys all know this, but in popular literature, in what book does the wormhole appear for the first time? The concept of wormholes was introduced to the public by Charles Dodgson, otherwise known as Lewis Carroll, the Oxford mathematician, and most famously the author of... Tell me, the author of? Alice in Wonderland! John! Alice in Wonderland had wormholes. Yes, Alice in Wonderland had wormholes. Lewis Carroll, also a mathematician, author of Alice in Wonderland and Through the Looking Glass. When Alice puts her hand through the looking glass, she is in effect entering a kind of Einstein-Rosen Bridge, connecting two universes, the strange world of Wonderland and the countryside of Oxford. I've never read it or seen it. Alice in Wonderland? Oh, it's a famous book. It has the Einstein-Rosen Bridge. So now you have more reasons to read it. It was realized, of course, that anyone who fell through an Einstein-Rosen bridge would be crushed. Something about playing croquet with flamingos. What does that mean? I don't know what that means. Would be crushed to death by the intense gravitational force enough to rip their atoms apart. Passage through the wormhole to a parallel universe was impossible if the black hole was stationary. It would take another 60 years before the concept of wormholes would occupy a key role in physics. So Einstein and Rosen came up with Einstein-Rosen Bridge and this concept of wormholes, but they didn't become sort of more cooler until later on when string theorists started to work on it. There's a really cool colored film here on YouTube, The First Alice from 1910s. Really? Those guys were high on all kinds of drugs. Who? Who are you? Who's high? Who's high? What's flamingos? What do you mean? Eventually, so guys, this is the summary. And it's the end of this chapter anyways. Eventually, Einstein gave up this idea. So this unified field, I'm betting LSD. Playing croquet. Oh, playing croquet with flamingos is from the book. Oh. I don't know the book I read it, but it's been a while. Eventually, Einstein gave up the idea, in part because he could not explain the richness of the subatomic world. So, it's all very well to say that subatomic particles are tiny black holes or quantum particles are tiny black holes and try to do the physics like that. And he came up with a very cool concept with his grad student, Einstein-Rosen Bridge, the wormhole, which is also in Alice in Wonderland. It was all very well to do this, but the richness of quantum mechanics was difficult to represent with this theory. It was very difficult to represent. He could not entirely explain all the curious properties. There were simply too many features of subatomic particles, for example, mass, spin, charge, quantum numbers, etc., that failed to emerge from his equations. So he tried and failed. You know, even Einstein can try and fail. It's fine. His goal was to find the picture that would reveal the unified field theory in all its splendor. But one crucial problem was that not enough was known at that time about the properties of the nuclear force. So the strong force wasn't really known at that time. You know, that would also have to be part of the unified field theory, of course. Einstein was working decades before. Data from powerful atom smashers would clarify the nature of subatomic matter. As a result, the picture never came. So he always liked to picture it. He always liked to come up with the sort of thought experiment and the picture that would show him the simple, you know, simple to him, but simple also in general in terms of the picture explanation of what was happening. He liked to do that, and quantum was not a very simple picture. If he wanted quantum mechanics to fall out of his equations, then he would also have to get quantum mechanics properties like the spin and mass and charge, and all of these different features of the subatomic particles would also have to come out of his equations, which is a lot of work, and that's really difficult, and it did not quite get there. So this is what the story of the unified field theory is. It did not really get there. Even now, it's not really there, you know? What is the strong force? That's the force between the subatomic particles inside of a nucleus. There's force between proton and proton and proton and neutron and neutron and neutron as well. It's the force of the quarks. You know the quarks? Do you know about quarks, Reese? Basically, there are three, let me think about it. Yeah, there are, so in part, so we haven't really, some of the greatest men in history were junkies. Are you talking about drugs? I don't know. Maybe. So basically, this is the end of this chapter. This chapter was called The Unified Field Theory and Quantum Mechanics, or the Quantum Challenge, or something like that. Oh, you're right. I mean, the concept of wormhole is from 1928, but Alice's Adventures came out in 1865, so he couldn't have been influenced by that. Oh, I didn't think of the timeline, but thank you for sharing, John. Actually, that's a good thought. I don't know why this author, Michio Kaku, thought that that was the influence for Lewis Carroll. Or mechanisms? What do you mean, mechanisms? Are you still asking about something, Reese? Hi, Hamid. But he created it, right? Maybe I misheard. Wormholes? The Einstein-Rosen Bridge can be viewed. It represents the first mention in the scientific literature of a wormhole that connects two universes. It's the first mention of a wormhole in scientific literature. The guy who made Alice in Wonderland might have independently come up with wormholes in fiction, but then wormhole in scientific literature. I think the author means that the wormhole in scientific literature for the first time is Einstein and Rosen Bridge. That's the work. I don't know. I'm going to make a cup of tea. My tiny brain is overheating. Oh, shut up. You're contributing to the discussion. But yes, make your tea. But I don't think your brain is tiny. I think you're important part of this discussion. Hoffman synthesized LSD. He was a physician, not a physicist. Oh, yeah, I don't know anything about drugs, man. That's not really my department. Hi, too. Hi again. It was derived from mold on bread or something, wasn't it, John? Yeah, I think now he's asking about LSD. So basically, unfortunately, it was too difficult, it was too complicated, and Einstein didn't really get the unified field theory work completed. It was too hard. And for all of quantum mechanics to fall out of a generalized theory is not an easy task. And also to describe all of the properties of quantum mechanics. But then I was going to answer the question of the strong force. I think I did it. It's the force within the nucleus. And also, Reese, we haven't really talked too much about particle physics. So, guys, I'm covering the topics of the 20th century, like the physics of the 20th century, because that will give us a very strong foundation for more recent physics, like physics of the 21st century. Because, of course, all of this quantum stuff has now evolved into the standard model of particle physics. And also, there is BSM, beyond standard model particle physics. We can talk about those things too. We will talk about those things as well. But all of this should be helpful in that discussion going forward. LSD is so different than drugs. Okay, I see. Sorry, I don't really know too much about LSD or drugs. It was derived from mold, yeah, fungus on rye. The idea of wormhole in Alice is retroactive. Got it. Imagine the STD back then. Okay. Lice was a big factor. That's why people used to wear wigs to hide their mangy hair. Ooh, Kayla is giving us some facts, some information. On April 1943, Hoffman accidentally ingested LSD and became the first person to experience its psychedelic effects. Oh, okay, I had no idea. Sorry I had to give that info since... Oh, good, thank you, Kayla. Bicycle day. Yeah, he had a trippy bike ride home. Really? Wow. Goodness. So, Reese, do you know about the fundamental types of particles? I'm just asking out of curiosity. I will cover it at a future discussion. But because you asked about the strong force, I thought I'll mention there, at this point, we categorize particles as leptons, quarks, and bosons. It's very insightful. I need notifications for your channel. Yes, please come to the live streams. We will go live again tomorrow, Sunday, I've been going live on most days. I think I just took off on Monday and maybe Tuesday, and then I've been going live every day almost. Wednesday, Thursday, Friday, Saturday. So yeah, come to our live streams. Love to have you, Kayla. And love that you participated and gave us so much information. Thank you so much. And yes, please, if you subscribe and then do some kind of bell icon thing, I think it will send you notifications. Just act like I know nothing, which is not... Oh, come on. No, that's not right. So in our particle physics discussion, we will cover this. But basically, the way these different particles kind of interact is different. So we'll get into more about that. During Einstein's time, we didn't really know about all of this. Particle physics is more new. Okay? Yes, but stop spreading misinformation, Reese. You clearly are a very educated person. Yes, Reese knows a lot, and he comes to these live streams and he contributes a lot. Gaslighting was originated, but the gas is released from the cold burning stoves which illuminated the light in the front yard. Oh. Actually, teaching as if someone knows nothing is the best. No, 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 no. Reese knows a lot. I think I actually get a lot of people who know a lot. And it's very nice discussion here. You know, because you might not know a specific thing, and that's fine. We all know something, and it's good. It's good to share knowledge in this on this platform. Because everybody is an expert in something. You might just not know some other thing. Like I didn't know about this gaslighting or LSD or the date of Alice in Wonderland. I've not been to college. You've not been to college? I just love science. Oh, wow. Great. That's awesome that you love science. Perfect. Yes, there is a diversity of people who are on the live stream, and I love it. That's great. I've learned a lot myself on these streams. But at some point, Reese, things will be. It's good that we covered. Sorry, it's good that we covered quantum mechanics here today a little bit, because we will take it forward, and we will also cover. I'm waiting to do this because I want to finish all the 20th century physics first, but basically going forward we will also cover particle physics and my field as well, particle astrophysics, because actually what I did my PhD in is particle astrophysics, right? It's a different than all of this, but I find it to be more interesting and fun to cover the foundation of all this stuff, you know, from the 20th century, because it was a very exciting time. And a lot of these sort of kind of learning about it historically is nice too, because you see the developments and it gives you that extra insight, which hopefully helps. And it gives you an introduction to the topic, because later on, when we talk about particle physics, you'll see a lot of this kind of helping. And I can talk about my own research too at some point, which is particle astrophysics. But I think it would be kind of difficult to, you know, consume that if you didn't cover all of this other stuff first. So that's why I've held off on the 21st century, more recent stuff until later. But yeah, really quickly, there's unless I'm missing one. Or ordinary matter is just leptons, quarks, and bosons, right? Electron is an example of a lepton. Neutrinos are an example of a lepton. Quark is what makes up the protons and neutrons. There can be like up quarks, down quarks. And then photon is like an example of a boson. So basically, particle physics further gets into all these different particles and what they all mean and how they all interact. There's an entire branch of physics now dealing in these tiny particles, and some of them are fundamental. Well, sorry, they're all supposed to be fundamental. It's because we realize that some of these particles break down into further particles, like the proton further breaks down into quarks, that then led to sort of this plethora of particles. Oh yeah, that's a good idea. A tree chart connecting all these parts. Yes. Maybe I should I think I'll work on some materials to help with the discussion. That would help as well. The book has been helpful, but yeah, it would be good to give it some more formalism and some more structure and understanding. I think my connection I think my internet is complaining. So if things get laggy, it's because of that. But basically, we will cover more things that have to do with how different fundamental particles interact. You will see how that interaction is different as well for different particles, and more details to come on that. And so you'll see how Einstein, what he was trying with the unified field theory, was hard also because he was ahead of his time. Not a whole lot. There was a lot of other things that came after him that we now know about the different particles. And even then, it's not like we have, even still, we still need to solve, as I mentioned before, the top two mysteries of the universe right now, which is dark energy and dark matter. Those are still unknowns. So even though we've learned a lot about ordinary matter, quantum mechanics has helped to open up a whole field and given us also particle physics, the standard model of particle physics, and now there's also beyond standard model stuff happening. But all of this still has not solved the puzzle of dark energy and dark matter, just so you know. I'd like to know more about the experiments and machines / observations that aided in knowing about these subatomic particles. Ah, that's interesting. Okay. You want to know about the experiments that give us the evidence. Okay, I'll make a note of that. That sounds good. That sounds good. Yeah. We should spend a little bit of, so it's good you got an introduction to some of these people today, Bohr and Schrodinger. Dirac, we covered a little bit more in a previous live stream. Heisenberg, Max Born, because I think we'll get into a little bit of a deeper dive into quantum mechanics one of these days, and we can cover the experiment stuff that you're asking about. And maybe we can get a little bit more into what Bohr did with a specific example of the hydrogen atom, because he's the one who did that. That might help a lot to illuminate it in the way that makes sense for you. Because it'll both be sort of an experiment flavor as well as the information about quantum. Yeah, see, I feel like the problem is machines are easier for me to understand. Yeah, I understand that people learn in different ways, right? So it's totally a thing where people learn in different ways. That has to be acknowledged. And quantum mechanics, when I talk to people and they realize that I studied physics or study physics, they're always like, oh, that's so hard, or what do you do with it? It's not a lot is known. Not a lot is known about physics topics, like the deeper or the more modern topics. And so I feel like you get any pizza rolls in the freezer? Not right now. I don't. But the problem is that quantum mechanics is not, I mean, I don't know, is it really taught in high school or in any normal education type things? So I feel like it's such an interesting field, but most people would not really learn it in their as part of their education. So that's why I think it might be good to think about how to present it. So I'll give it some thought. Thank you for all your contributions and comments. It's like 4 now. Thank you for staying up with us. Nicholas, do you work with some specific devices in your particle? Yeah, so the experiment, Kayla says it's 2 a.m. for me. Ooh, so you're behind. Kayla, I'm trying to, I know another Kayla. I think she's a different Kayla though, because their time zone is different. I think I've learned more in your streams than I did in the entirety of high school. Aww, about quantum you mean? Yes. This is my first time seeing you. Okay, Kayla. Welcome, welcome. Welcome to the channel. Welcome to our live streams. Please do join us again going forward. We have another Kayla. I have another Kayla that joins, I think, from the UK, and maybe another one from the US as well. So that's why I wanted to ask. But 2 a.m. would mean that sort of like the mountain time or something. Got it. I'm glad that this is helpful. We will get into it more if it helps. Quantum mechanics. I realized that, actually, I realized that quantum mechanics, that's why I think I'm in Montana. Oh, God. That's awesome. Montana is one of my states that I'm missing. I'm missing 19 states. Oh, somebody blocked me. That's why I had a bad week. Ugh. It's like a stupid dating thing. I do sing, yeah, I can sing. Guy troubles. It's just been the worst. Yeah. Yeah. I had the most weird experience this week. Thankfully it's done, but I don't really usually experience these things because I don't really try such things. But not only was it crazy, but now I've been blocked. It's a first for me to be blocked. I think I'm blocked. Yeah, I'm blocked. Oh gosh. I don't even know what to think of it. It's too much. Nick is being a flirt. Who is Nick? And FK boys, they're so selfish. Hope it won't be considered espionage. So don't. Okay. So don't spill out too much just on general. Yes. Well, no, because my PhD, it's been some time. So it won't be espionage. Basically, I worked on a radio telescope kind of experiment. So this experiment was a bunch of radio antennas, horn antennas, to catch radio waves. So speaking of experiments, I worked on one. It's still a thing. It's an ongoing work, but the part I did is done and wrapped up, and it's been a little time. So it won't be espionage. It's fine. It's public knowledge, and we've published much of it. So basically, I worked on a radio experiment, and it's a bunch of horn antennas that we hang from a gigantic balloon in Antarctica, and we use the polar vortex to launch it and make it have these circular-ish trajectories over the continent of Antarctica, because we want to look at the ice and measure radio waves coming out of the ice from neutrinos interacting in the ice. So we use the ice as a detection medium. Yes, Cherenkov radiation. Yes! Reese knows. Reese knows about this. Oh God. Yes, I need to charge my phone. But yeah, basically Cherenkov radiation measurement from neutrino interaction in the ice is what I worked on for my PhD, and we used a radio telescope for it in Antarctica. So it's an experimental work, so we can definitely get into it. I can make a presentation on it for you guys. I have many, so I can do that easily. That's like easy peasy stuff for me. So it's actually good for me too to review all this old stuff from the 20th century, because once in a while it's good to remind yourself about all the basics and the foundational stuff. Because for my PhD, I mean, everything I did for my PhD should be very clear to me already. Like, I know that stuff, right? But also at the same time, sometimes what you know you might still have blind spots. So that's why it's always good to review and whatnot. Something to do with the equivalent of shockwaves. Oh yeah, Cherenkov. I read about it. Thank you. I would love that. Okay, great. I will present my PhD work soon here. That should be helpful. Also, that will give an introduction to particle physics, because so my hi Michael. Good morning, Michael. I remember reading about other cubic facilities deep inside the ice or earth to see the, yes, that's called ice cube. So the biggest experiment for astrophysical neutrinos, biggest as in most funded, $1 billion experiment is ice cube. It's called ice cube. It's at the South Pole in Antarctica. So there's a few different experiments for this in Antarctica. I'm gonna turn off this light because it's in my eye. There's a few different experiments for this in Antarctica. Anita, Ara, Ariana, Ice Cube. Yes, they travel faster. Well, the particle, the ball of particles travels faster than light in that medium, not faster than light in general. Thank you, Reese. You read my paper. She's intelligent. Oh, thanks. But yeah, basically, there's a few different experiments to that kind of takes advantage of this Cherenkov radiation type of stuff, and to there's no private chat in YouTube, thank God, or I would be blocked there too. I'm not good at that stuff, you know, so I get blocked usually. I got blocked, guys. So that's who you're dealing with. It's better to publicly talk about physics only. What do you think, is the Earth a ball or is the Earth flat? Huh? The Earth is definitely not flat. It's round. We've seen it. We've seen it. Well, that's true. It's not perfectly round. Thank you, John. Thank you, John. I don't know if I want this light. I think it's off. Off is better. So basically, there's a few different experiments in Antarctica. They all kind of have different scales and different energy regimes that they work in. I also have a chart that shows that. So it'll be very interesting for me to go through that with you as well. I've made slides on this many times, and I have this sort of presentation kind of already. So I'll work it together, put it together for you guys here. Earth is a geode. Thank you, John. Hey, Google, what is the shape of the Earth?
The Earth is roughly a sphere.
Roughly a sphere. So geoid. Yeah, there's an I in there somewhere. So there's a few different experiments, like I was mentioning, in Antarctica. There's actually something in Greenland too. Why did he block you then? I'm nosy. I want details. Oh my god. Oh my god. This guy was so like fast. He just moved. He was moving very fast at everything. And within this, let's just say, I don't want to get into too much details, but let's just say within the span of 6 days, he had my number and also blocked me. I'm still shocked. I'm still shocked. I'm in shock from this. I'm a peaceful person, so this type of stuff doesn't really happen with me much. So anyway, I'm blocked now. It all depends. Okay, Michael says, "Oh God, no." Anyway, at the bakery, at my favorite bakery. Now I can't even go to the bakery. Oh my gosh, Kayla! Kayla is like a mind reader. Yeah, I'm a little traumatized. Ugh. I think I have to Uber Eats the bakery now, right? I can't go to, this is my favorite bakery. It's the bakery I go to after the election. I blame the election. Well, the private chat is where I get blocked, Michael. So I needed croissants. And so I went to the bakery. And then now I'm shunned from the bakery too. I can't go to the bakery. Should I go to the bakery, Kayla? After this whole thing happens, 6 days of the number to the block with lots of drama in between. More drama than I can take. I was like, whiplash. You go. Be you and yeah. Thank you. I'm sad though. I'm kind of sad. Ugh. Now I don't even have the bakery. Why can't I have anything nice? I mean, I have lots of nice things, but whenever I try this sort of thing and I think that, oh, this will be nice. Oh, the bakery, I like it. It's not nice. That's okay. Just don't. Oh, I don't care if they know I'm sad. It's fine. It's fine. I'm over it. I mean, I'll be fine, regardless. But if they know I'm sad, well, yes, it's been a sad time thanks to someone. I'm sure. I'm sure I'm at fault. Because as well, but it was a shock to my system, I must say. Because now I'm blocked. And it is my favorite bakery. I think I will have to go back after some time. And I think in the meantime, I have to do Uber Eats from the bakery. But that makes me mad because Uber Eats costs delivery. Sounds like you just weren't compatible. Well, yes. Exactly. Yup. Indeed. This always happens. Yup. You liked him, but it was a shit. Aw. Yeah. 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 Whatever. You guys are so nice. You're so receptive to my life, issues. You can go to the bakery. They shouldn't judge, and the guy can get overseeing you. Stand your ground. Well, I think if I go now, he'll think that I'm trying to like chase him. I want the croissants, but I think if I go now, because I think the block was to like teach me a lesson. I know, it's so strange. Within the span of 6 days, so much shit happened. So my take on it, not that I'm saying I'm good at any of it. People are not really like this type of stuff is like not really my jam at all. This was probably like a date for me after years and years. That's why I'm sad. It's like, okay, I thought this would be a nice thing after like 3 years, and then this happened. So I think I'm more sad about that than anything. But thank you for your encouragement, Kayla. Stand your ground. But croissants are great, and I just think it'll be misleading. No. I think I do want the croissants. Okay, if there's one thing that's for certain is that I definitely want the croissants, and there's even some pastries. Okay, there's some good croissants and pastries there. I don't want to. I was a happy customer, and then, this happens. So I just want. At some point, it doesn't have to be soon, to go back and get some pastries and croissants and have my life back of the croissants. Croissants are great. He can get over his ego. I'm just saying he's probably thinking about you right now. Oh God, I hope Nicholas is not him. He's probably got some fake profiles. Because, yeah, that too is a thing. I don't think it's a you problem. Thank you, Reese. You're most supportive. Thank you so much. I understand. I'm sorry, girly. Thank you, Kayla. I've been there, I promise. I've also been there, sort of. But my overall experience is not that vast. Thank you for reading and explaining. Good night to Baji. By the way, did you watch Cosmos Possible Worlds by Neil deGrasse Tyson? Yes, of course. Yes, Neil deGrasse, good guy. Such a dilemma. Encounter Block Boy. And Block Boy? What does that mean? And have croissants, or be without croissants but free from the social anxiety. Right. Right? It's the best bakery in this neighborhood. That's why I go. Block Boy. Encounter Block Boy. But you know what? I think the universe will be kind to me and this situation will change. Because maybe he'll get a job somewhere else, you know? I think me and my croissants will be reunited. Oh, BBB. We should talk in code, honestly. We should talk in code. You never know who's watching. I'm a little scared, actually. That's why I didn't say much, but it is helpful to get your support. Keep going and don't think about what he thinks. That's the thing about standing your ground. Oh, yeah. Good. I'm hoping that this is too late for most people to No, I think it's too late. It's too late. I don't think they're here. I don't think they're here. BU and yes, thank you. I did stand my ground. I basically had some boundaries. And in the past, like when I was much, much younger, I might have like been less good about these. But now I'm like, dude, I kind of have my life together. I kind of have like a whole setup and a situationing and sorted. So I kind of like don't really want to be messed with and manipulated with and having like a bad experience of like disrespecting my boundaries. And so, yeah, they didn't like that. That's when it all falls apart, right? How old am I? I'm real old, Kayla. I'm 34 now. I'm from the last century. No way? What do you mean? My interaction with the sun is limited, in other words. I work in dungeons sometimes. Genetics, babe. Genetics. I know. A few years ago, they wouldn't let me into the hospital by myself. They would say, "Where's your parent?" You look like 25 or my age. I'm 27 and don't even feel it. I don't really feel 34. I don't think that goes away. Cuz like just think about it. Every year is just another year. I do things. Things happen. I work and then it's another year. It doesn't really do much. Like I think after a point your age is not that important. But I have grown a lot, I think personally from especially my failures. This being one of them now, it gets added to the list. But my friends are like, okay, it was so fast. It's like a 6-day thing. Just get over it. And I'm like a little bit sad though, because I'm like, I, I think I think that depends on the perspective. He probably They probably think it's my failure. I don't know. I don't know. You have to ask both the sides, you know? I'm a Libra. I can't be unjust. But I will say that I have noticed that if you have not too many, if you have boundaries and you're strong about them, which people are less strong about when they're younger, right? Especially young girls, like, especially young girls are taught to be a certain way, you know, like socialized differently, taught to be more pleasing, you know, people pleasing. So when I was, like I was saying to Kayla, when I was a lot younger, this might have been a different story, but now I'm kind of like really strong now. I don't really tolerate disrespect. So it didn't really work out. Yeah. So yeah. So yeah. Hi, Fuji. Besides, Baji didn't like him. Baji hid upstairs. That tells you everything. Baji was like, I'm gonna nope. Here's Fuji. It's hard to be assertive when you're a people pleaser. Yes, so I'm a recovering people pleaser. I think some of the people pleasing type of tendencies can be a good thing, like online, because like I'm a content creator and I interface with people. So to some extent, that's where I figured out like I should probably be a content creator because this type of shit actually helps in content. But in real life, I want to recover from my hi Babu, hi Shonu. I want to recover from my people pleasing because that really does not help me in real life too much. Although it is a sort of a survival technique, so in some sense it helps me. Same age, but so different. Same age. I like your name, BBB. So, in real life, I realized that with these types of, like, on the long term, even though people pleasing is kind of like a survival thing, in the long term, it wasn't working out well. So, I try not to do it. Like, I'll be nice. So, I think this is what's going on. Like, people expect me to be less assertive with the important things because I'm kind of like more lax about the less important things, less important to me, that is. People think, oh, she's nice, she'll just play along with whatever. But then when they realize that I don't, and I cut a bitch, then they really don't like it and they block me. Assertiveness becomes a survival thing the older you get. You have to protect yourself. Yeah, I think that's where I'm at now. It's not good at all. Like, I can't just, like, you know, yeah. It was bad. This week was kind of traumatic. I had to protect myself. So then they saw my assertive side and did not like it. But so Kayla said she's 27. Okay, so you'll relate. You've had enough time to experience the shenanigans. I hope not. I don't know. I don't know, man. Yeah. So Kayla, God, isn't it awful? Because I know that guys and girls kind of experience different things too. And the thing is, yeah, when, like, by the age of 27 or so, you've probably, unfortunately, right? I mean, some people are lucky. They just meet once, they date once, and then they're married and everything is great. But by the time you're 25, 26, 27, you've had plenty of time to experience, like, unfortunately, all of the. That's why it's so peaceful to just be by myself, do my work, be career focused and kitty cat focused. This is my life. Right, Fuji? Suji Baji. It's much better. Yeah, it's so nice. And I have my whole situationing with the thanks to the universe. I'm like, I don't need this drama. I don't think I can do this. But I was nice. I wasn't, like I said, I'm not the one who blocked first. I'm so shocked by all of it. Let's just say in short, everything was shocking. Everything was like too much, too soon, too quickly, all the time, happening. Too much, you know? So then when I was blocked, it was a little bit of a relief. I was like, oh, okay. Let's go back to my boring life, which I like. Oh, Fuji's purring. Nothing is better than this right here. My baba right here. Kayla, how did you know? That's what happened. Love bombing, right? It is love bombing, right? But is it love bombing even if they're from a different culture? I was giving a what's the word, benefit of doubt, because they were in a they're from a different culture. Like a different, totally different culture. So I was like, maybe it happens there. But yeah, that's called love bombing. Narcissistic do that. The rejection will be easier to overcome than the loss of croissants. 100%. 1,000% My older son is 23. Okay, Nicholas. Yep, doesn't matter the language, it's a human psychological aspect. Right? I don't get it. Why would they do that? You might have dodged a bullet. Mhm. Hell yes. It was making me very worried. It's a neurotypical thing? Narcissistic pig. You guys are so funny. Should I ask my friends to pick up the croissant? I'm telling you, from day one, I've been thinking about the croissants. Uh, you seem to really love me. Well, I don't know about the UK. In the US, it's really bad. The whole dating culture is like awful. Yeah, yeah. Kayla says I'm neurodivergent. I think I am too. I think I'm weird. Pretty much I've never really been totally normal and totally like my peers. I think I'm neurodivergent as well. I think I'm sort of a target in that sense. It's awful in America. You're mega high functioning. Reese, thank you. You're so nice. BJ. BJ, you missed out on our dramatic conversations today, but thank you for being here. Some of my mentors and colleagues kind of tell me that. I had really good mentors in college, especially in undergrad. More than in grad, in undergrad. And then in work, sort of. Ugh, it's lonely. I think for the neurodivergent people, we have to be. So, Kayla, nice to meet you, sister. We have to stick. First of all, I think women have to support each other. And the neurodivergent, special, neurospicy, special women and men have to be there for each other. I'm so glad I met all of you. I feel like I feel a little better now Because I think when people go through something, it's kind of like it's a little hard unless you get some support. I told a few of my friends, ugh, they all like hated the whole thing. Um, they were very supportive, and so are you. Because it's still on your mind, so thank you for your support. We should definitely stick together and be there for each other. I really think that as you get older, it's really about, I mean, not even older, just in general, it's really about getting a good group of friends going for yourself. Like for me, I'm so happy that I finally, I think, have a strong foundation. Thank you, God. Thank you, universe. Touch wood, where I have like a good group of friends. I like where I'm living. I like my life. I've done a lot of work on myself and to get my life to be the way I want. And it's still like ongoing, but I think I'm at the point where I'm a little bit much more like unfuckwithable. I hope YouTube doesn't ban me for these bad words, for these curse words. They're not necessarily bad words, but I'm much more like that. And that's thanks to having a good group of friends and a community like this, you know, have my own thing going on. It helps a lot. So I'm happy to be there for my other friends like this. And that's what I'm saying. I'm here for you. I feel it. It's hard. Men don't understand the emotional requirements of women, myself included. You think so? Well, I don't mind if the emotional aspect develops over time. Could not contend with the unfuckwithability. Yeah. As soon as they realize that, they don't really like me anymore. So it's very lonely. So it's lonely. No, but actually, the nice thing is I have so much more time for my work and career and YouTube and you guys, who are, of course, part of my life now. And it's kind of nice. I'm meant for, you know, bigger things. So I think it's one of those things where you can't really have everything at the same time. Whatever. Bigger things. Poor BBB. That's the good part. Focus on that. Exactly. Thank you. I was sad that I'm like, why did I even do this? You know, like, shit. Like, what a waste. What a waste of time. I mean, it's only 6 days, but still. Um, so I felt bad. But now I'm like, yeah, it it's good to realize what's the good part and focus on that indeed. We will be there for each other. Thank you guys. But yeah, so you were saying that men don't require understand emotional requirements of women. Well, I was willing to develop those over time. I even said, let's just slow it down, take it one day at a time. But no. Here is Fuji on my lap. Baji's over there sleeping. I think Suji, I don't know where she went. I love you guys' comments. Thank you. Oh, Kayla. Even for Kayla, it's late now. So let's meet again tomorrow. He just didn't see you by the sound of it. Yeah, the depth of me. Yeah. Time means nothing when it comes to special connection. It's a lot of work and has many social and mental variables affecting it. But I believe you will find love that's meant for you. Oh, thank you. It's okay. I was like fine by myself. So I'm glad. Back to that state now. I was also about to say it's late and I love your mind. I can't wait for your next live stream. Thank you. Thank you so much, everybody. Yes, my phone's gonna die. So I've got to go to bed myself. Yes. Go to bed. Have a good night. Thank you all. Thank you for being here. Thanks for your support today and the lively discussion during the live. Good night. Thank you. Thank you, Reese. Thanks for the stream as always. Enjoyed it very much. Thank you. Thank you, thank you, thank you. See you next time. Have a good day. I didn't ask too much about your day. We'll see you soon and hear about how everything is going. BJ says, haha. Nice to see you, BJ. Bye. Bye, bye. Bye.